Did you know that there's an energy source called fusion? That if you took this bottle of water and you converted its energy through fusion, it would be the equivalent to 100 barrels of oil. It's a university just being woke again. We should close these places down. This is what people think about what we're doing? No, no, no. What we are doing is we are the engines of economic prosperity.
Yes.
That we're the seed parts of economic prosperity and economic dominance of this particular political system. So you're telling me fusion is really one of the most important, because on paper it can basically solve everything of our energy problem forever, forever. It's such an important thing. We have one single project in the entire world, and if it fails, then we're toast.
In this episode of the 632 Nanometer podcast, Misha, Xinghui, and Mike meet MIT Professor of Nuclear Engineering Dennis Whyte for a nuclear fusion deep dive. Dennis was a longtime director of the MIT Plasma Science and Fusion Center, PSFC. He is known for his dogged effort to make practical fusion energy a reality using smaller, cost-effective fusion reactors enabled by advances in high-temperature superconductors. Dennis is the co-founder and scientific advisor for Commonwealth Fusion Systems, CFS, a billion-dollar effort to commercialize fusion power. The conversation goes into the nitty-gritty of fusion reactor design trade-offs, why fusion is so much harder to make economical than fission, the practical and administrative realities of fusion research, and much more.
Dennis, could you tell us what brought you to the field of fusion?
Yeah, actually, it dates back to, if you can believe it, when we had paper newspapers, and I grew up in rural Saskatchewan, Canada, but there was a provincial newspaper, and put in, for some reason, in the same place where the comics were, like Snoopy and things like this. It was Ripley's Believe It or Not, I think was the name of it. And it was my first introduction to fusion. I was like 15 or 16 years old, and they had this classic graphic of fusion. Did you know that there's an energy source called fusion? That if you took this bottle of water and you converted its energy through fusion, it would be the equivalent to 100 barrels of oil. And I'm looking at this, is this real? Is it real? And so that was my first introduction to fusion. I actually remember it, right? And I thought, that is amazing. And I asked my high school teacher if I could write my term paper that was in physics. I think it was probably 11th grade, so it was like 16 years old, something like that. And could I do it on fusion? And I scoured libraries and things to try to find, no internet, right? To try to find information on it. And I wrote up on that, and I actually have the paper in my home, still in my closet at my home. It was I got an A on the paper, but I'll always remember the comment from the teacher. It was a great job on this, Dennis, but this just looks too complicated. That was, which I have to say was excellent foreshadowing of the things that I have ended up working on in my career, which is trying in some sense to uncomplicate it a little bit.
What was like the first textbook or your favorite textbook that kind of got you deeper into the subject?
Yeah, actually it was interesting. I kind of lost, while that was interesting, I went to school in engineering physics in Canada and University of Saskatchewan. And I kind of accidentally came back into and got an interest in fusion, was because there was a significant amount of study going on, particularly because of aurora borealis studies, which are essentially plasma studies. And I took a class that had to do with basics of plasma science, but it also covered fusion. I don't think it was even a textbook. I had an awesome professor in that, and started reading on it, started actually doing real work on it rather than just superficial looks at it. And I just got totally fascinated by the field. There's a few textbooks that kind of cover it. There's one by Chen from UCLA. That's usually a pretty accessible book, just because it has fairly simple math in it, and it goes through the key concepts in plasma physics. But it's interesting, actually, fusion itself there's a book by my colleague, Jeffrey Freiberg, but he only wrote it a few years ago, which tried to cover more of the concepts in fusion energy. It tended to not be, honestly, a very accessible subject matter. Fusion, I mean. right? So you could find things on plasmas, but fusion, they tended to be very pretty complex introductions into the field, almost solely meant for graduate students, not for undergraduates. Yeah. One of my ideas is actually at some point to sit down and write a textbook which is accessible at the junior and senior level for STEM students. And myself and my colleague, Zach Hartwig at MIT, and a few others as well too, we've actually put together an undergraduate course which tended to be rare itself actually in fusion and going through the primary concepts. So anybody's basically nuclear engineering, physics, any kind of STEM discipline would be able to get through it. Yeah, but it doesn't exist yet.
When you were studying plasma, were you really scared by the numbers which are required for the fusion reactions? For example, the temperatures, it's like in the order of, what is it, 100 or 10 million?
100,000 C. Yeah.
100 million. Million, right?
100 million,
Oh,
no,
100
100
million,
million Celsius, yeah. Let's use scientific use, 100 million Kelvin. Well, no, because actually the energies which are involved are actually very small. I mean, the moment you start looking at anything in nuclear science, it's like everything's in the, I mean, that's actually how we know almost everything about nuclear science. You start building accelerators which start at around 100 kilovolts for a fundamental charged particle. That means energies of around 100 keV. The first classes of accelerators were there up into the MeV range, so about 1 million electron volts. That you can build that actually. In fact, we have one where undergraduate students build something called a fusor, which is essentially a small internal accelerator effectively through a grid that's around those. And you can make fusion actually reactions with that. In fact, we had a student who came in and him and his twin brother actually built one of those when they're in high school. So the energies involved are actually not that hard to imagine, because 100,000 volt, a couple 100,000 volt accelerator you can put together in a
It's essentially, it's the
laboratory.
lack of the slow particles that makes the temperature so high. That's essentially what's going on.
Bingo. This is what's confusing often about fusion, is that people go, oh my God, it's so energy. It's like the energies involved, we've accessed those since the days of modern accelerators, since the 1930s. The difficulty is Coulomb collisions, is that the way to accelerate particles to those energies, and that's literally why we use that unit, right? We use electron volts, which is basically just the energy which is gained by a fundamental charged particle over that number of volts. So if you look at the peak and the cross-section for DT fusion, which is the most easily triggered fusion of those reactions, it peaks at around 100 keV, 100,000 electron volts. And so you take that and you put it into, it's one of the first things you teach students, right? You take that, you put it into, let's say we do it with deuterons, and then you'd have a triated target, which just means it's filled with tritium in some way. And you basically hit this, you accelerate that, hit it into the target. It's like you will make fusion reactions, DT fusion reactions, because it's at a sufficiently high energy that it can overcome the Coulomb barrier and trigger the nuclear reaction. The difficulty is the Coulomb collisions, because you're accelerating a charged particle, it comes into solid matter, and what it starts doing is that it undergoes collective Coulomb collisions, particularly with the electrons, and the electrons are at room temperature. And what this means is that you can calculate the rate of energy transfer that happens between this incoming particle and the electrons. And what that ends up is just heat, because you're just collectively exciting all the charged particles in the solid matter. And approximately you get something like 1 in every 10,000. So what that tells you is the rate that the incident deuteron slows down. And then you can calculate also the rate, what's the probability per unit time of the fusion reaction occurring. And what you find out is that for every particle, you have to put about 7,000 or 8,000 deuterons into the target to trigger one fusion reaction. But you spent 100 kilovolts of energy already accelerating it, and the energy gain is what, 10 MeV, so it's about 100 times that. So you're doomed. You cannot make net energy systems by just simply triggering fusion reactions. And it's all because of Coulomb collisions. So Coulomb collisions happen, right? The collective effect which is going on of this particle interacting in the so-called over Debye lengths. And so the immediate and in fact, you can go back and even normalize this and say, what if it even wasn't at room temperature? What if in fact you allow the background medium to have arbitrary temperature? So then you do that, and what happens is it's a feature of Coulomb collisions, is that Coulomb collision frequency decreases as energy. Mm-hmm. So this is the other quick calculation you do, which is very counterintuitive at the beginning, but you calculate this, and the reason is because when particles are interacting through Coulomb collisions rather than essentially like solid sphere collision model, it's an action at a distance, and almost all of the exchange of forces happens at the closest distance of approach. So if particles are going faster, they basically spend less time in the strong part of the Coulomb proportional or attractive field, and therefore as they go faster, they actually interact less with each other, not more, which is very counterintuitive. But you actually go through that, you can calculate that, and then you say, oh, well, let's imagine now it's not room temperature, it's rather a temperature, an ensemble temperature up at temperatures like 10 keV. By the way, the translation is 1 electron volt is approximately 11,600 Kelvin. This is why we always just multiply by 10,000, and then you roughly get the temperature in SI units. 1 electron volt is about 10,000 Celsius. That's roughly where ionization occurs. And so the numbers I'm talking about of 10,000 10 keV, that's 100 million degrees Celsius. That's where the conversion comes from. Anyway, so you actually go up to temperatures like 10 keV or 100 keV, and you calculate, even if you allow the particles to be super fast so they collide less, it turns out Coulomb collisions are still hundreds of times more. And what I mean by that is that the exchange of momentum and energy is hundreds of times faster than what you can get from the energetics that you get from the fusion reaction, basically the probabilities. The relative cross sections of Coulomb collisions, which are essentially the scattering collisions in any medium like this, are always way, way bigger than the fusion reactions. So what does that mean? Conceptually, very important, is that it means you must allow the collisions to occur because you can't avoid them. It's physically impossible. And when you let lots and lots of collisions occur in a closed system, then it becomes a temperature. It's not an energy. And this is the key thing. By the way, we do a horrible job of teaching the difference between energy and temperature. They're absolutely totally different things. And what that means is that, in fact, they are different things because temperature is only defined through thermodynamics. Yes, yeah, right. So it has to do with energy, but it's actually a different concept. Anyway, so in the end, that's actually why you get to the point where you must have a temperature. That's what we call it thermonuclear fusion. Just fusion is easy to occur out of thermal equilibrium. It must be in thermal equilibrium, and you must have a temperature. Thus is the requirement for energy or confinement. Because if it's a temperature, this means it must be isolated from the laws of thermodynamics. It can't be in direct contact with something that is actually a much lower temperature, or otherwise it will transfer all of its heat into that. Thus, this is when you see about fusion, you go, what is the hard thing? You ask this question, what's the hard thing about 100 million degrees? The hard part is not the average energy of the particles. The hard part is keeping it thermally isolated from the terrestrial environment.
So what you're saying is actually that if these things were tuned a little bit different, if the losses were lower and the energy of the Deuterium-Tritium reaction was a little higher, it might have actually been very easy to do fusion, like net energy fusion. We just live in a universe where it's not easy. That's
You live in a universe where there's only one place naturally that has fusion energy gain, is in the center of stars for exactly that reason. Yeah. But it is cool to think about that. You can actually go and say, what would a fusion reaction look like that would actually get you to net energy? And it is about that. If the cross section was like 100 times larger than what it is right now, then you're right on the precipice of in fact just being able to get energy out of the system like that with just a simple accelerator, and we would have fusion. It's approximately that, right? By the way, we have a name for that. You know what it's called? Fission. because the deuterium-tritium is an amazing nuclear reaction. It has a peak cross-section of about 5 barn. Typical nuclear scattering collisions are about 1 barn. It's a really large nuclear cross-section, except with one exception, except for the thermal capture type of cross-sections, which are like fission, where a neutron gets captured at room temperature, has about 1,000 barn. So this is again where the factor of about 100-ish comes around, and you do that. Oh, and it can occur at room temperature. Like fission is just like ridiculously simple in some sense compared to fusion. But what's interesting to me always, that I always, because I teach both about fission and fusion, is that this leads to some very interesting consequences. It's not just the confinement of the, like in the end, you actually, by the way, you go, oh, as an engineer, you think it's like fission, While it can occur at room temperature, I better isolate it and confine it in a proper way so that I'm actually controlling the power output, the physical assembly of the fuel and so forth. As all those things are true in fusion as well too, they just happen in a different place. In the fusion power plant, like all of that engineering happens by definition outside of where the actual energy source is occurring, which is in the plasma. So nuclear fusion is this interesting push together basically of plasma science, because you must understand plasmas, because the medium in the end is plasma and nuclear engineering and nuclear technology, because it has to be nuclear technology, which is actually the constructed thing that basically allows this energy source to interact with the engineering world, right? So if you look at our department, you'll see most of us have some kind of combination of training in those two things. Yeah.
So what was your first foray into hands-on plasma fusion or fusion research? Was it theoretical, or did you have access to a facility where you could actually conduct small-scale experiments?
Yeah, actually, I dove right into the big one. So what it was, and this dates me, when I was an undergraduate, they didn't let undergraduates do research. Undergraduates will break things, so we don't want them to be touching any of my expensive equipment. I probably did like a plasma lab. I probably like a Langmuir probe or something like that when I was an undergraduate. But what happened was, after I finished my engineering physics degree, I dove straight into fusion, into confinement. And what that looked like was that they had just completed the construction and commissioning of a tokamak, which is one of the primary fusion confinement concepts, just outside of Montreal. And it was interesting. It was done by something called the National Institutes for Scientific Research, Institut National de Recherche Scientifique, which is like the research arm of the University of Quebec. So it was very focused on developing it in Quebec, which is interesting because their other partner was Hydro Quebec, which is one of the world's largest electrical utilities. And actually the device was built at the Hydro Quebec research facility just outside of Montreal. So I just dove right in because that experiment had just started and they were looking for graduate students. I was lucky enough to be, in fact, I would think I was literally the first student to arrive there to start working on that, and also the first student to get a PhD out of it. So I just dove right in. It's like I was already I basically started doing measurement techniques on thermonuclear plasmas like right away. So I just jumped right in. Yeah.
Oh, so that was fantastic timing,
which was really
and
fun. Yeah.
the co-location.
Yeah. Again, I think it's interesting. Modern education in STEM provides so much more opportunities for undergraduates to do research. And like I tell all my undergraduates, there is no substitute for getting in a lab and going and doing research, because it's totally, while it's connected, it's an academic activity, obviously, it's totally different than solving PSATs and sitting in a classroom. You have to go experience it to understand both about whether or not it's for you and find out what your skills are in it, right? And for me, like, I remember I moved a long ways away from home, and also no texting or anything like that. We had a time every Sunday that I would call my mom and dad back in Saskatchewan, because that was a big deal back then. Yes. So they put me right to work. I already started building a small instrument. It was basically an optical instrument to start measuring things about what were going on in the plasma. And I think it was probably like a month in. Like I told my mom and dad, I said, "Oh, I found it. This is what I'm going to be doing for the rest of my life, almost for sure. It's because this is what I was waiting for, right? Like, honestly, university bored me a little bit. It was like, because it wasn't piquing my interest and my curiosity, and also my activities about thinking about how do you go and do something. So that was an interesting experience for sure. And then in about a year, I published my first paper, and I actually constructed it in an experiment. It was basically something called laser ablation. It's thin film laser ablation. We use this as essentially as a perturbation technique to measure what happens when you put particulate matter into the plasma and basically follow it around. It's like a tracer essentially. But what you had to do is, we realized nobody had actually quantified the atomization. So this basically, it's a short pulse, like YAG laser or something like that, hits into a thin film target, a couple microns, and technically they said, oh, and this atomizes all the particles. But I realized nobody had actually ever measured it. So I actually came up with a technique that was a new idea, that I basically came up with an idea of using nuclear activation analysis. It gets complicated, but I basically came up with this new idea about how, so I built a little test stand and just characterized everything about how these particulate matter worked and published that. There was that moment too. It's like looking at the data and realizing no human being ever had actually seen that. I mean, it wasn't that big of a deal, but honestly, but that feeling of knowing, oh my God, like I'm the first person to actually see this data, interpret it, and then understand it so that other people can understand it. It's like a drug almost. It's like this feeling of discovery was very quickly that I also understood that's what I wanted.
Could you perhaps uncover some of the aspects of like research work which has been done maybe at that time or nowadays? Because tokamaks or the fusion machines, they're quite complex. So it probably takes generations of students to see what is happening. Also, I guess the environment, since it's probably, I understand, like quite big groups. Yeah, if you can open up, how does the research work organized?
Yeah, it's an interesting one. It's one of the, so fusion clearly sits in the big science category, right? So in this way, it has features that is interesting about making it. The way I look at it as a professor now is, how do you make it accessible enough and tractable enough for students to access it, right? There are kind of toy, almost fusion things that you can do, but they're not really that relevant, honestly, to the things that you're doing for fusion research, like to build a tokamak. Like you can't, well, I shouldn't say that. One of my MIT students built one in his kitchen.
Oh, was this during COVID? This sounds like a COVID project.
It almost worked. Yeah, exactly. But he was a very special guy, actually, around that stuff. One of the interesting challenges as an educator, and then also for students as well too, is it's a little daunting, actually, the sizes of the groups and the sizes and the timelines of the project. Think about LIGO and all the students that, because the timeline of it, the implementation of it, in some sense, the patience that it takes is just wow, right? But there's always things to uncover. But the key thing, like a lot of those other ones, is that people think, oh, fusion is studying plasmas, but actually making and understanding fusion is extraordinarily multidisciplinary, because the first thing I started to learn was optics and atomic physics, because that's basically almost one of the only ways that you can actually measure things which are going on in the plasma. A very common entryway into this is not, hey, starting student, build your own fusion device. It's, oh, here, we parse down this problem. Here's a particular subset of a problem, and kind of parse it down to that so that it's actually something tractable in the laboratory and as a study. And then what you do collectively is that you bring this in, and that's actually the cool part of fusion, honestly, which I love, is that then you have within a larger group, this is another piece of the puzzle that you're putting in. So just looking at measurement techniques, like in a fusion device, like a tokamak, there's something on the order of 30 or 40 different kinds of measurement techniques which are going on to tell you all kinds of things about what's going on in the different parts of the plasma, different features of it, and so forth. Is that when the student brings a new kind of tool, you're putting that in and making it part of the puzzle That's the other cool thing for fusion students is that you then add to the knowledge base, but you also use all those other capabilities. Because again, it would be physically impossible for the student to deploy this entire diagnostic suite, but then they get to use it, right? That's a very common way to do it. Of course, now there's a lot more being done computationally because modern computing has made so many more of the challenges attractable from a computational point of view. But again, like you don't start these from scratch for the student. It'll tend to be, there's like a code platform or something, and then the student will come in and this simplifies it, but basically make some module or some addition that goes onto it or use it in some unusual way that hasn't been done before. This is now becoming a very common pathway actually for students to do their graduate work in fusion. Because the fundamental things are kind of covered already, you're doing those other things. And then there's a whole class, which is really cool, which is that in fact, the nuclear parts of fusion are actually now coming more to the forefront because of the accelerated timelines that we want for fusion. And interestingly, in many ways, because that technology is so behind plasma and confinement ones, it's less mature. So it's more like the old days almost. It is more like hands-on laboratory experiments. So that's a really cool, I think, diversification that's happened in fusion education as well. And right now, in fact, at MIT, on Albany Street, there's a whole set of experiments that are like the early stages of trying to understand or get direct empirical data on some of those. And those are literally students building things and deploying them in the lab. That's really interesting, yeah.
What's the mix of backgrounds of these students? Are they all physicists or engineering physicists, or do you also have mechanical engineers, electrical engineers? Because these are very, very complicated machines for which you need specialists on all of these fronts.
Yeah, but you have to realize nuclear engineering itself already includes all those disciplines. Like nuclear engineering is actually not an engineering discipline in the traditional way. It's actually an accumulation of mechanical engineering, chemical engineering, physics, and you're saying, we're actually, if you look at the people in a nuclear engineering department, we actually have backgrounds that are all around all of these different things. But then the way to look at it, but you specialize because the application in nuclear technologies is just so different than anything else because of, well, almost back to your first question, like the energies and the ways that the particles and everything interact with each other is in a scale which is just totally different than standard engineering. So that tends to be, and that actually is the other thing that is, students ask me all the time, what would I study to get good at fusion? The answer is everything, pretty much. Almost the only thing we don't do is bioengineering, and who knows, that might be coming down the pipeline as well too.
From like scientific engineering point of view, maybe it's some simple questions like regarding like the fundamentals of the fusion. Why is it deuterium and tritium reaction? And maybe also my other questions would be, how do you feed in the energy and get it out from the system?
I'll start with the fusion reaction one, right? What is fusion, right? It is essentially an assembly of a new nucleus compared to the starting ones. And there's a whole variety of these, including ones, by the way, which take excess energy. So using accelerators, you can make all kinds of, so we call this the Q value of the reaction. So what this means is that you take the starting rest masses of the particles, and then you take the final rest masses of the particles, and if there's a deficit of mass, then there's a positive Q value, and you just figure this out through E equals mc squared. Delta E equals delta mc squared, because c squared is a constant. And then, but you can also have an excess actually of mass. That actually means it requires external kinetic energy to trigger it. There's a whole class of reactions like this. So for fusion energy, we're only interested in the energy gain ones, and they have to have reasonable cross sections at reasonable energies. And what that means is that we tend to look at energies which are around 100 keV to an MeV for the reactions that are in play. And I'll get back to that actually part, because that tells you about how you heat and so forth. So when you look at the reaction, what this tends to be is the nuclear energy binding curve, basically from low mass goes up really quickly and then falls over. And then iron is the most stable nucleus because it has the highest binding energy per nucleon. And that's what fusion distinguishes itself for an energy gaining reaction. Fission climbs down the periodic table and we go up, right? So what you tend to look at automatically are the hydrogenic species because they're the lightest ones. And in particular, almost every fusion reaction that you're interested in ends in helium. And this actually comes from nuclear physics, is that nuclear physics of the binding energy, it loves pairing of protons, neutrons, and the two of them as well too. Helium is perfect because it's a pair of a pair, and basically it has an extremely high, in fact, on the curve, it's an outlier. It's like really, for a low mass element, it's very, very high. So basically fusion wants to make helium to make those reactions. And so
the reason you want
Yep.
low mass is because of the Coulombic forces between the nuclei.
Exactly. Right. So in general, of course, the number of proton in the nucleus, the number of charged the protons are scaling in the lower part of the periodic table. It's scaling something like the atomic mass. And so the more protons there are, then the higher the Coulombic barrier by z squared, right, in whatever the interaction is. The features are you want low atomic charge, hydrogen, one, the best, right? And you want the combinations to end up in helium because then the nuclear physics is very favorable to high energy gain. Yeah. So it's not universally like that because there's a few other ones, but if you look at, so immediately you go hydrogen, nope. Because a direct Coulomb collision actually doesn't end up as that, which is strange because you think, isn't that what the sun is made out of? But the stars actually use a different cycle actually to make fusion happen. And it occurs at a really, really slow rate compared to what we do in terrestrial fusion. So while we say we're making a star on Earth, we're actually not replicating the nuclear process that actually happens in stars. In fact, there's a couple of different kinds of cycles that happens in stars, but it's because these occur at a really, really slow rate, like millions of times smaller than what we're doing. Okay, so back to this other one, you look at the other combinations, you go, oh, deuterium, which is perfect, right? Proton and neutron in each of them, you put them together, that directly makes a helium particle, except it doesn't. From nuclear physics reasons, when you combine these, it actually branches off into two different categories. In one, you get a proton and a tritium. Hydrogen, a single proton, deuterium, proton and neutron, tritium, proton, two neutrons. Helium, two protons, two neutrons. And there's something called helium-3, which is two protons, one neutron. Those are the key players. In the DD one makes proton and a tritium because it's conservation of nucleons. It's just the rearrangement of them. And the other ones, you get helium-3 and a neutron. Those turn out, because those are not as stable as the helium, you don't get as high energy gain, right? That one is interesting.
How were all these energies and reactions originally figured out? Is it theoretical or are these experimental?
Accelerators.
Okay.
Accelerators.
So all the
Accelerators,
information that was built up around all these reactions first was built up in accelerators, and then all this optimization could happen.
Yeah, all the nuclear physics, these things are, in fact, it's interesting. When you get to really low energies, it's actually hard to measure the cross-sections accurately. It turns out to be one of the interesting science issues. And you do for all the different combinations, DD, you can also, there's actually deuterium and helium-3 actually have a very interesting fusion reaction as well too. Deuterium and helium-3, and it makes a helium, which is fantastic, which gives it very high energy gain, and a proton. But it's interesting, its Coulomb barrier is a little bit higher because one of them is helium and that makes it 4 times higher, the Coulomb barrier. Ooh, okay, that makes it, and in fact, its cross-section is less than those other ones, but it has a very high energy gain. So all of that is good. There's another one called p-boron-11, very famous as well too. So there's a proton with boron-11, and if you do the masses, you realize, oh, that actually makes 3 alpha particles, alpha meaning the helium, right? That has a very high energy gain as well too, but the Coulomb barrier is so high that it peaks at much higher energies, more like almost an MeV around on those ones. So you asked this good question, what is so special about DT? So it turns out it's the extra neutron that's involved in the tritium produces actually a nuclear resonance. What it actually is technically fusing into is helium-5, which has a it's an unstable nucleus. It has a very short half-life. But because of the presence of that extra neutron, there's a very strong resonant reaction that occurs at around 100 keV. In fact, it's another one you can do very quickly. Just take a proton and another proton, try to get them to internuclear distances, right? So it's just the Coulomb repulsion. And internuclear distance is a couple of femtometers, so a few times 10 to the minus 15 meters. And of course, the Coulomb barrier, the Coulomb energy potential is scaling inversely like the separation distance. So it's just the fundamental charges squared divided by 4 pi epsilon naught and then the distance. So everything about Coulomb barrier is just like the energy potential gets higher as you have distance of closest approach. And you realize that that number is around 300 keV approximately, something like that. So you go, oh, well, that's the minimum temperature or minimum energy, minimum energy that's going to be required to actually get them to fuse. And that would be approximately correct for like a deuteron or something like that. And it's actually not that far off except for 2 reasons. One is quantum tunneling. This is a key concept that actually requires, and of course this stems from the fact that they're not actually hard spheres. They actually are, through quantum mechanics, they have wave functions associated with them. And what happens in quantum tunneling is that there's a finite probability that in fact the wave functions interact, that the particle, it's basically an evanescent wave, and it makes it through the Coulomb barrier. So this gives you finite probability at energies which are lower than the Coulomb barrier, that's a quantum effect. But there's another huge effect, which is a major resonance that happens at around 100 keV, and that's the big one actually. So what happens with DT is that it has a cross section. Almost all those other cross sections have maximum values less than a barn, but because it's got that resonance at very low, relatively low energies, 100 keV. It has something like about 200 times the cross-section of any other fusion reaction. And because it makes a helium, you actually get very high energy gain in it. So its energy gain is almost 17.6 MeV. And because the cross-section is peaked at around 100 keV, it turns out in a thermal system, this is one of the things that you have to work through, is that in a thermal system, which means there's a lot of particles with a temperature distribution, a Maxwell-Boltzmann distribution of energies, is that even when you have a temperature of around something like 10 or 15 keV, the tails of the distribution in this thermal system actually have a very high probability of fusing. So in the end, when you have a thermal system, and you look at, in fact, the temperatures which have been achieved in the laboratory, which go up to about 20 or 30 keV, have actually been achieved in the laboratory. DT it actually has a power density, which just means how many fusion reactions are happening with their energy release. So what's the power that is being produced in the volume is over 100 times larger than any other fusion reaction. There you go. So that's why you use DT. And it's because for a power... So this means that accessing net energy gain is a lot easier in DT, but you also get higher fusion power density, which is actually the key economic driver actually for anything that is in fusion. For all of the interesting challenges of doing DT, it's very hard, very difficult to overcome factors of over 100 and all these different things. Yes.
So this is essentially the lowest energy to start fusing. That's the beauty of it?
Yes. So this is something called the Lawson criterion. So this is really important, is that in the end, fusion, because it's a thermal system, actually has a rather simple way of indicating how you get energy gain in the system. And what this means is, this is derived by a scientist called Lawson in the 1950s, is basically in thermalized systems, you go, oh, so the thermal system basically sets the rate reaction. It's like a chemical in chemistry, right? You put things together at a particular temperature, then is that you can calculate the rates at which they will happen. It's the same in fusion, right? So you can take all these different reactions and calculate versus temperature what their reactivity will be and then what energy. But then the other key part of it is that how does the system maintain power balance, because by definition, it's out of thermal equilibrium with the surrounding environment. What you do is then you have to consider the way that it will heat, right? This is the question that you ask. How does it heat? Primarily in a fusion power plant, it heats itself. And the reason it heats itself is because in a plasma environment, if you've contained the deuteron, whatever it is, the deuterons, the tritons, whatever the plasma species that you have, is that the reaction is that when it makes a helium, when it makes the alpha particle, the helium, by the mass distribution between those, it contains a relative fraction of the energy. That's where fusion energy is. It's just in the kinetic energy of the particles that are made by the fusion reaction. It turns out, by the way, which is another interesting one, there's no gamma rays or anything like that emitted. It's just literally in the kinetic energy of the particle, because these things are in their ground state. So you do that, and what you do is you calculate this reactivity, and you realize, oh, whatever comes out as a charged particle, essentially the helium or the alpha particle, that is participating in Coulomb collisions with the background particles themselves. The assumption is those charged particles get heated up by the fact that they've got something which has much higher average kinetic energy, because it's out of thermal equilibrium now with the background plasma. It's a very energetic, it undergoes Coulomb collisions, which you can calculate, and through those Coulomb collisions, it gives its energy back into the plasma fuel, into the medium. So that is the immediate thing that you do, is that you can start calculating this, is that you go, there are two things that happen when you get the fuel together and you start making fusion reactions. One of them is it starts to heat itself. We call it alpha heating just because it's coming from the alphas that are produced by the fusion reaction. It's just helium, it's an energetic helium ion undergoing Coulomb collisions with the background plasma. And
self-sustained
what's
reaction,
that?
so it can keep igniting.
Well, yeah, so it's important to remember, yes, exactly. But very importantly, and very distinguishing itself from fission, is that helium is an incredibly stable nucleus. It doesn't want to undergo any more fusion because it's already basically at the peak of its stability. So there are fusion reactions for helium, but they have to go to much higher energies than what we achieve in this. And in the end, what you get is actually 1/5 of the energy, because it's the inverse of the mass ratio. So when you get DT fusion, there's 5 nucleons involved because of the deuterium and the tritium. You get 17.6 MeV, and by conservation of momentum and energy, 1/5 of the energy ends up in the thing that's got 4/5 of the mass, which is the helium particle, and 4/5 of the energy ends up in the thing that's got 1/5 of the mass, which is the neutron. So the neutron is at 14 MeV, and the alpha particle is at 3.5 MeV. Mega electron volts. Remember these other ones I was talking about, is that the energies were in the orders of 10 to 100 keV. This is the energy gain that you get in fusion.
The neutron is lost because it can't be confined by magnetic fields. So it just...
Well, actually, the neutron is lost, period, because this is the only reason why you only consider charged particles, is because it doesn't undergo
Right, it's not going to
Coulomb
interact.
collisions.
Yeah.
It's not even that it's not being affected by the magnetic field. In any fusion system, the neutrons will just go out. So the neutrons, because they have no electric charge, do not undergo Coulomb collisions. So what this means is that it must undergo nuclear collisions to basically interact with anything. In other words, it has to hit into nuclei, right? And what this means is that the rates of interaction are millions of times smaller than it is for charged particles at the same energy. So neutrons interact very, very weakly in solid matter, let alone in plasmas, which tend to be more tenuous than that. It's like a typical neutron going into a piece of steel will travel 10 centimeters before it undergoes a single collision.
What do you use as moderators for these escaping neutrons to shield the...
That's the point. It's not moderation in the classical sense. So this is how fusion distinguishes itself from fission, is that you go back to that other part. It sustains itself through heat. That's the only, because that's what the plasma wants. It wants to keep the conditions necessary that the soup of plasma basically stays at high enough temperature that the reactivity stays. That's actually what the Lawson criterion is. It's just thermal equilibrium. It's just like the amount of power going out of the system is equal to the heat coming into it, and it comes into thermal equilibrium by definition. So I'll get back to that one about the moderation, right? And in the Lawson criterion, there's one other escapable feature that's a power loss, basically, in the system. And remember, I told you that the rate of reactions of Coulomb collisions is much higher than what's going on in terms of how much you get back from fusion. But that's not an energy loss, it's just an energy exchange between the particles. But, well, you guys know a little bit about physics, but it's charged particles undergoing acceleration, because that's the point of the Coulomb collision, right? And particularly the electrons, because they're very light, and that's in plasmas, by the way, we were talking about the deuterons and the tritons. In a plasma, you must have an equal number of negatively charged particles for it to be a plasma. The electrons are nearby, and they're very light, and they undergo very large acceleration, and they actually emit radiation. So this is called Bremsstrahlung radiation, or breaking radiation. It's a continuum kind of radiation. In fact, it goes that instrument, when I was a grad student, the first thing they had me start building was measuring Bremsstrahlung radiation, it turns out. So it's an inescapable thing, because it just arises from the Coulomb collisions themselves. And plasmas tend to be very transparent. They don't reabsorb the energy, because these are typically like X-ray kind of energies, things like that. You go do that calculation, it says, and that's the simplest one, is that basically the rate at which the plasma heats itself through alpha heating as compared to the rate that it loses power by Coulomb collisions is really simple. It's because both of them are binary processes, so they both depend exactly like the density squared. So the density drops out of the equilibrium equation, and all it depends upon is the reactivity rates of the losses of the radiation, which depend on the temperature, and the rate at which the fusion reactions occur, and that's the temperature. And then the constants which come in, which are these energies. And you calculate that, and it turns out for DT fusion, it's about 4.5 keV. And what that means is that at infinity confinement, like perfectly confined systems, you still need around 4.5 keV, which is approximately 50 million degrees Kelvin, to get energy balance in the system. That's called the loss in credit. And the other ones, the other fusion reactions that we just talked about, you can calculate the same thing. It's a classic P set that we give to starting graduate students. They're more like around 25 keV, which is the minimum temperature, actually, that you can get to get energy balance in the system, let alone high gain. In fact, what's interesting in these systems is that you never actually design a fusion power plant at that, because that's just barely getting net energy gain. In fact, you have to go to conditions in which the energy gain are much larger, like approaching ignition, which means that the gain's going towards infinity.
How do you...
So that's actually the reason for those. And recognize there's no chain reaction, right? That's the other reason why fusion is so safe, right? No chain reaction. So it does not sustain itself by the fusion reactions itself. It sustains itself by recycling the heat. So anything that disrupts or basically perturbs the containment of the confinement of the energy or of the heat, all fusion stops, because the plasma is out of thermal equilibrium with everything else. So it basically just turns back into a gas, and everything goes back to room temperature, and there's zero fusion.
How do you measure these crazy high temperatures? I guess you're not taking...
Optics. It's all optics. Actually, that was one of the reasons for one of these measurements, is that if you, so everything is optical because you can't put it in a physical object in place. So a whole discipline, actually, a subdiscipline of fusion is essentially optical measurement techniques. And we use everything across the spectrum, all the way up to hard X-rays. So for example, X-ray detectors that measure the energy distribution of the photons coming out of the plasma is a direct measurement, essentially, of the thermal equilibrium of what's going on in the plasma. So you can measure things like that. We can get ion temperature measurements by putting in trace particles. For example, in a 10 keV plasma, the ionization energy of the fuel is the Rydberg energy, 13.6 electron volts. So everything, the fuel is fully ionized. But if you throw in a krypton or a trace amount of argon or something like that, these have 18 or 36 electrons. Even the thermonuclear plasma can't ionize all of them. So what happens, in fact, I was just talking to a colleague, what we tend to use are crazy atoms that it's basically an argon, we use argon a lot because it's just convenient, is that argon, 18 electrons, has a nuclear charge of 18 as well too as an atom. We strip away 17 of the electrons. And the ionization potential of that, because it's increasing so strongly, increasing as the nuclear charge squared, it has ionization potentials in the multiple thousands of electron volts. And so in fact, what this means is you can do X-ray spectroscopy on, it's essentially a hydrogen atom, but the proton is actually replaced by an argon nucleus. All right, but then it acts like a Bohr atom because it has a single electron, but it's just the energy levels go way up into the X-rays. And what that allows you to do is, if you do careful measurements of this Doppler broadening, tells you the ion temperature in the system, which is a really cool way to do that. We also even get things like rotation from Doppler shift. It tells you a whole bunch of things, what's going on. And then and then there's other things in between, and we go all the way down, in fact, into the microwave range. And it's because the other thing that's going on in magnetic plasmas, magnetized plasmas, is the particles are executing cyclotron orbits. And the cyclotron motion actually has a harmonic, it's a harmonic oscillator basically. So it actually transmits at the gyro frequency of things like the electrons, and then the system becomes optically opaque to that. And so what we use is we actually use radiometry. It's basically a black body, so you can just use radiometry and get directly out of this also the temperature of the electrons in this way. So everything optical and remote and distant.
This was I was going to ask, can you dope the plasma to make it less transparent to X-rays or whatever, so you can absorb some of the X-rays that you're producing?
No, yeah, it's a good question, right? It would just have to get
too dense.
So we call this optical thickness, yeah, and it's not even, even in the other systems, the other extreme of this from magnetic confinement is inertial confinement. And this is where the density of the fuel, it requires higher density basically to increase the opacity, but also the temperature matters to it. But there, the mean free path for X-rays is it just leaves the system, yeah. So in any practical system, it's an energy loss, which is in it. Now there's another category of kinds of emission. In the magnetic field one, there's also something called synchrotron radiation, which is basically this happens in high energy particle accelerators. This is coming from the fact that the electrons are executing a large circular orbit and they're actually emitting particles. This actually has bigger implications at higher magnetic field and higher density for the Earth. And those ones can actually be partially reabsorbed by the plasma as well too, because they bounce around like an optical cavity almost inside of it. It actually turns out to be a really hard physics problem. Some of the best minds actually, because it's this crazy, it's semi-transparent, and so the way that the plasma actually reabsorbs the power is very unclear. It's actually one of the cool, we'll probably start seeing the impact of this in the devices that we're building with Commonwealth, because it turns out that this effect has a higher impact at high field, because the bending radius gets tighter, basically. Yeah.
And getting to more like overview pictures, there have been like decades, probably 60, 70 years of research in fusion. And then where are we now in terms of extending? What are the next challenges?
Yeah. Well, recognize from a physics point of view, fusion has been a spectacular success, right? So you ask these good questions. How are we going? We went through the physics basis of this. You have to provide containment, right? And what does this mean? It means that you have thermal populations, and it's interesting. It comes from, this is one of the things to teach all my students right away. It's very counterintuitive. The thing that's required is hot electrons in the system. And the reason for that is because the electrons are like the canary in the coal mine, right, of this. Electrons are in many ways harder to contain because they're lighter and faster. They're 2,000 times less massive than the charged particle. But you say, well, aren't we fusing the nuclei? Yeah, but the electrons have to be along for the ride. And so it turns out the electrons, in fact, it goes all the way back to that thing about an accelerator going into a target. The problem is the electrons, actually. They get heated up. The electrons must be hot, otherwise they will just bleed away all of the fusion energy, right? So you must get hot. And what that means is that you have to get them hot enough in the thermal, then their so-called collisionality, or the rate that they suck up the fusion energy, starts going down a lot, like T to the inverse 3/2 power of where T is the temperature. So after saying all that, what does that mean? Is that if you don't have approximately 1 or 2 keV electrons in the system, thermal electrons, that's the other way we do it. We measure these with something called Thomson scattering, which is basically a laser probing technique, which actually just measures the elastic scattering of the laser light off of the electrons and how they Doppler shift. This gives us an independent and very localized measurement of the electron temperature. This has to be around 1 or 2 keV, which is, again, the translation of that, that's around 1,000 electron volts or about 10 million degrees Celsius. If you don't have that, you're toast, basically, from the power balance point of view. And we have ways of measuring it. And what's cool about this is that I counted them up the other day. There's 6 things that we've made that actually have done that. And that's pretty impressive, like 6 very, very different kinds of things that have done that. And when you do that, you almost always get fusion reactions as well too. So we've actually made confinement things that have done those things, and they're quite different from each other actually as well too. And it actually comes from the Lawson criterion. The Lawson criterion in the end tells you you get a temperature, and then the other requirement is that you have to have a product of the time scale at which the energy is contained and the density of the fuel. And it's weird that it's a product. It actually doesn't care about the absolute number. It just cares about the product of the two. This is where fusion gets really confusing, is that what happens is that all of these different things that we use, like magnets and lasers and all that, what they're actually doing is accessing the Lawson criterion at an incredibly wide range of densities and energy confinement times, as long as the product of them makes up. Inertial fusion is basically super high density, and by definition, you're not, in some sense, it's called inertial fusion because you're actually not confining it. You're confining it on the inertial time scale of the fuel, which tends to be like a few nanoseconds. It's like, oh, so the density has to be super high to meet the Lawson criterion. Magnetic fusion is all the way over on the other side. It's basically about 10 to the 10 times less dense, but it tends to have energy confinement times of around a second. We've actually done those things and made thermonuclear plasmas and all of those, and some things in between actually, which is also really cool. So it's like, wow, that's like amazing. And in many of those, particularly inertial confinement and magnetic confinement, remember, that's the containment requirement, that's the plasma physics requirement. And then there's the nuclear requirement, which is basically the Lawson criterion, which is what I just said, is that namely, you get the fuel to a state that it's hot enough, it has high enough density and energy confinement time, that basically starts to heat itself at a significant relative level. So almost all of these fusion concepts have made fusion. The thing is that we were creeping up towards being able to get to satisfy the Lawson criterion, which is the power balance. And at power balance, if you get it to the right point, it starts to make energy gain in a thermalized system. And that is an obvious requirement for a power plant. This is again where it gets more technical. It's like these things have made thermonuclear plasmas. We've made thermonuclear fusion reactions at very large rates. But you must satisfy the Lawson criterion to be able to actually make a power plant, right? And that's actually the era that we're in, is that right now the different concepts are actually racing towards ever higher and higher gain. And so tokamaks were hovering at a gain just below 1, like really close, like to break even. And what happened at the laser fusion experiment at Livermore a few years ago was they actually got energy gain significantly above 1. But from a science point of view, what was really important is they turned on alpha heating. And alpha heating was spectacular. Alpha heating spontaneously increased the temperature of the fuel by 50%. It went from, without alpha heating, is it around 8 or 9 K? In fact, the papers are just coming out in Nature right now. It came out about 8 or 9 keV, and it jumped up to about 15 or 16 keV. By the way, measured by our office mates on Albany Street, because it was basically measured by an instrument that came out of the MIT group that's deployed there. So amazing, right? Oh, wow. And that's actually what Spark does as well, too. So Spark is actually and ITER on the magnetic side are the ones that actually say, we just needed to make that last push over the hill to get energy gains which are relevant for a power plant. And for a power plant, you need energy gains order of 10. It's not such a hard limit, but it's approximately that. And the simple reason is because in the end, these are thermal systems, so you can't directly capture the fusion energy. You actually have to put it through a thermal cycle, because mostly what you're capturing is neutron energy. And what that means is that if you take engineering and thermodynamic limitations into play, then the engineering gain of the system in the end tends to be about a quarter of what you get of the scientific gain. And having a power plant at around an engineering gain of around 2.5 or 3 is feasible. You can't build it at 1 because it's too marginal, right? And that's actually where, that's like the next frontier, right, of where we are. So we're taking these different concepts. Spark is probably right now the leading one, using high magnetic fields, and achieving a place where you can reliably see what a high net energy gain plasma looks like. Because even the NIF ones, the ones out in California, are not actually routinely accessing that. They're actually a factor still of 50 away from relevant gains for that particular approach. So that's really like the summary of where we are, by the way. And it was an incredible feat of not just science, but of the integrated multidisciplinary engineering of all the things we talked about. Like building these contraptions is hard. Measuring what the plasma is doing, coming up with computational models that describe about how they work. All these really hard things were done across these variety of different approaches. And now you can see the light towards actually that the scientific accomplishment means that you start handing it over into the engineering side of things, right? Because the scientific requirement is the starting point, but in order to make an actual power plant, you need to start handing this over. And you can go to the equivalent of this, like think of like a coal power plant. I can sit down and I can calculate the rate at which coal will burn, given a particular temperature and a something. But the thing that actually makes energy is an engineered system that has heat transfer pipes. And in fact, that engineering is the thing that limits typically about how fast you can burn the coal, how effectively you can extract the energy. Fission is exactly the same way. Knowing the nuclear cross-sections is not building a nuclear reactor. You actually have to build all the fuel assemblies and the coolants and all the things that actually get the energy out. And that's where fusion is right now, because we're on the precipice of actually being able to, across a variety of different techniques, of confinement techniques, seeing a scientific gain that actually merits the thing of going after getting high engineering gain in the system. After particularly spark works, that's going to be, in my opinion, like the race. That's going to be the fusion technology race, because those things will really, really matter actually as to how well the power plant will perform to produce energy.
So would be the first big milestone for Spark be to demonstrate alpha heating sustainably?
Its design point is around a plasma gain of 10. And what that means is, so what you do is, this also is a little confusing, but what you do to understand energy gain in any kinds of these systems, you have to draw a boundary around something, and then you count the energy across that boundary both ways, in and out, right? So you'd ask actually a question like, how do we heat this thing? I said, primarily it's internally heated, but you still have to provide some external energy and heating to get the system to the right physical state that it actually does this. So we count the things that are, and actually in the end, for a variety of reasons, it's kind of like an amplifier. You actually don't run the amplifier fully open. You actually always control it a little bit. So you're always putting a little bit of power. Typically, this is radio frequency. The way you get energy into the system in magnetic confinement is you also use photons. It's just that it's radio frequency waves that actually have resonances that actually interact, and that's the way. So you literally have launchers and transmitters that actually provide power into the plasma. That's the typical.
To microwave your plasma.
In Spark, yeah, it is. It's actually, one of them is the same, near the same frequencies as what you have in your microwave. So you think there, it's like you're not sticking something into your turkey, right? So this is near Thanksgiving. You're actually using the bombardment of the microwaves, and that actually exploits a resonance of the microwaves at 2.5 gigahertz with water molecules. That's actually how it's heating up. So we use similar kinds of resonances. Our primary one is we use FM radio frequencies. They're about 100 megahertz. And then that means we have launching structures which are specialized to basically do that. And then what this ends up doing is it actually resonates with the heavy charged particles spinning basically around the magnetic field in the center of the plasma. Anyway, so that's how we get power in. So what is this Q? This Q is you basically count the amount of energy or power, depends on what system. In magnetic fusion, it's continuous, so we just count the power. So the power that's going across the plasma boundary as compared to the total of the fusion power that's being made. And that fusion power has to go across that boundary in thermal equilibrium, because by definition it's isolated, right? So all of those, the neutrons, the alpha heating, in the end, it all has to come back across that boundary. So you just basically count those up, and what that says in spark is you have 10 times more fusion power being made than the amount of external power that you're putting into it. So what this means is, but if you remember my quick math about where the energy balance is that 4/5 of the fusion energy actually just leaves because it doesn't interact with the plasma because it's in neutrons. The 1/5 actually is the internal heating source, and this is set by the mass ratios in DT fusion. So 1/5 of that power is actually going to heating the plasma. So in spark, at a gain of 10, what this means is that you just divide by 5. If you think about it, what this is this is the internal energy gain in the system, and it means the amount of self-heating from the fusion reactions is 2 as compared to the external heating that you're putting in. Aha. This is actually why you build a device like Spark. It's because you realize all of these other amazing things that we've done, but we've actually never let the system be self-determined from a power balance point of view. Because we are controlling this by putting in an external power source. But when the plasma starts determining how much it's heating itself, and this is where the cool stuff comes in. Why is it cool? Because it's a coupled system. Because what sets what sets the alpha reactivity? What sets this? It's actually the physical condition of the plasma itself. It's set by the density and the temperature of the fuel. Well, what sets the density and temperature of the fuel? Thermal equilibrium. Well, what's setting the thermal equilibrium? The amount of heating and losses that are going on. And what's setting the amount of heating that's going on? The fusion reactions themselves, which are set by the density and temperature of it. So it becomes a coupled, closed system at that point. And that's really the primary thing that we need to see to make sure that that looks okay, because that will be required in any fusion power plant. It has to be dominated by self-heating. And so now you're giving up a very large control knob, basically, about what the thermal equilibrium state of the plasma is. Now, most of the time when we simulate this, it looks great. The plasma loves being heated because it's out of thermal equilibrium. It loves heat, right? But there's a whole bunch of subtleties to about how the alpha particles will interact. In fact, it's interesting, there's something called the burn instability. Will actually try to elevate the density and temperature so fast that it actually burns more. So it's not a runaway in a sense like a fission device would be, but in fact it could get too hot or it might get too dense, and therefore it could violate perhaps like a stability limit or something like that, or you're not controlling the amount of fusion power that you're getting out of the system. Really key it's the equivalent of hitting criticality, although it's from a completely different physical mechanism than what you have in fission. It becomes a self-determined system, right? And any scientist understands that's quite different. So that's really like the precipice of where we are. We're going to see that. That's also ITER. It wants to do that. There's some other private sector fusion companies, but that is like the starting point of thinking about fusion power plants, because that's going to be requirement of regardless of what concept you use. Does that make sense?
So how do you actually extract the power or the useful energy? It's very interesting. You mentioned that 4/5 of the energy is lost by neutrons. So how do you get whatever is left over and then convert it to electricity before it gets further?
Yeah. So let's start with the neutrons, actually. Well, let's start in general. In fact, there's a paper, in fact, I'm writing right now about this. So it turns out there's a great simplification in fusion, and it also comes to be about its challenge, is that fusion by definition requires isolation and confinement of the fuel itself, and it's a volumetric process. So whatever you use in fusion, there's a volume of something making fusion, right? And there can be zero terrestrial objects inside of that volume. So you just think about this from a high level point of view, you realize, all of fusion has a volumetric source, and then there's a surface, an engineered surface around it that is the place where every joule of energy must come up. Yeah. So that varies in the different concepts, but that's where the engineered component is. So you can just think of this then as an areal power density, that namely there's a amount of power per unit area which is being pushed out to those two things. And so let's go back to the DT fusion. So this varies extremely significantly between the two different kinds of heat that are coming out, or energy that are coming out. So let's start with the alpha particle. So the alpha particle, remember, that's the concept. The alpha particle has charge, it's contained in the plasma, but it actually just thermalizes, it just gives its net energy. So imagine the plasma's at 10 keV, it's at 3.5 MeV. So it's like 300 times more energetic. So it gives us energy back and actually just ends up slowing down and becoming thermal with the rest of the plasma. So then we can just, so what does that mean is that the heat goes in, the energy ends up as heat in the plasma. So that means it's how the plasma, which is just this collection of Coulomb of charged particles, touches this extends surface around it and transfers energy into it. So this is something called, so when plasmas touch solid objects, this is called a sheath is formed. It comes about, it's the negotiation that happens between the fourth phase of matter and the first phase of matter. So this happens in all low temperature plasma, anything that you have. And what it actually ends up being is it's an electrostatic barrier which is formed by charge separation in the plasma medium itself to actually enforce ambipolarity at the surface. Ambipolarity just meaning that basically the negative and positive charged particles come out at the same rate. And the way that it does that, it regulates itself by forming an electrostatic barrier, basically, to the negative charged particles on the outside. In the end, what this means is the plasma loses its energy by the fact that it sets up this sheath, this electrostatic barrier, and then particles basically fall through this electrostatic barrier into the material. And so it's literally just impact. Like, so if I'm a surface, I'm going, how is this energy arriving? There's just energetic ions basically dropping through the height of this energy barrier is set by the plasma temperature, it turns out, and it basically just bombards into the material surface. So that's one way you get energy. It turns out the boundary part of the plasma tends to be at around the ionization potential of hydrogen because it's cold out there. It's not where the fusion is occurring. It's basically the coldest. In fact, if you've ever seen a picture of a fusion device, you'll see an ambient light that's all the way around the edge of it, but you see nothing else. That's because that's where the ionization is occurring. That's at 10 electron volts, which is so it's like 1,000 times less temperature than where the fusion is going on. So say this cold outer boundary about where things are going on. And at 10 eV, it turns out approximately the energy at which the particles will go is something like 5 to 10 times that temperature. So what's actually happening is the particles are dropping through about 100 volt accelerator into the material. And the rate at which that happens basically sets the power. So at 100 volts or 100 eV, this means the charged particle only goes like a couple of monolayers of atoms in it. So it is literally a surface heat, right? That's all. So that's one way energy gets out. So how do you get that energy out? That comes into a surface. This means how do you get it out in equilibrium must be through thermal conduction. So there has to be an object that has high thermal conductivity and hopefully thin, so that you can promote heat conduction and get it out to some kind of a coolant, right? So the typical pictures you would imagine, you get some engineered surface, and then you have a coolant pipe like right behind it, and you make this really thin. The charged particles bombard the surface, and you basically extract it. So it's surface. So now you can see why this is multidisciplinary. By the way, this problem looks like it's mechanical engineering. It's heat transfer, right? It's like the same thing as like how do you get energy out in an internal combustion engine? By heat transfer. It's a really, really weird environment. There's a thermonuclear plasma a couple centimeters away from you. Yeah. The other way to get the heat out of the plasma is in fact photons, because the plasma is composed of negative and charged particles. We already talked about this thing that I said one of the ways we measure what's going on is the release of photons. So stars are being lost by the Stefan Boltzmann law, right? So basically the equilibrium there is set by black body radiation, Planck radiation, which is coming from the surface of the sun, which varies like temperature to the fourth power, right? That's actually why the sun is so stable, because it has such an enormous temperature variation. It turns out there's an equivalent in plasmas as well too, is that plasmas have heat conductivity, which depends the temperature to the 5 halves power as well too. There's very, very strong nonlinearities and all of this. What these tend to be are in fact thermostats, which actually regulate the temperature of the medium around on these things. So in the end, but you're right, is that in fact, the interesting thing, the subject of a lot of my recent research is in fact optimizing or maximizing the allowed fraction of power that comes out as photons rather than as charged particles. Photons are way, way better and it's easy. It's because what's the problem with those charged particles coming in and hitting a surface? And have you got that? See, I can't stop being a professor. It's like, it's interesting. They're at 100 electron volts. Oh, what's the binding energy of, you probably don't think of, I think of matter as being basically a collection of atoms and energy wells. Yeah, it's a few, in fact, what vaporization and so forth is just actually surface atoms which get enough energy based on thermal energy distributions to leave the surface. It's like, oh, they're an order of 5 electron volts. So this means the medium of the plasma interacting with this, unless you get the plasma super cold, it actually literally vaporizes the material from, but we have a special name for this, we call it sputtering, because it's actually an atomistic process that there's a finite probability for every ion that falls through it, you eject a particle back up into it, and this means you're going to start remaking the surfaces. Another way to think, it's almost like it's a corrosive medium, but it depends on kinematics, right, around on that. A lot of my research was actually in this area. It's a very complex system itself, just around. So this is why you like photons, because photons they come with energy, but they don't have really, technically they have momentum, but it's not enough to actually cause the ejection of these. So having photons come out, how do you do that? What you want is a lot of inelastic collisions and processes that basically make photons, which typically have photon energies which are like that of the electrons in the plasma, but the electrons are sort of keV, so these are basically X-rays, right? And so X-rays also have penetration distances into normal matter of only submicrons, right? In fact, that also turns out to just surface heat. It's everything. So in the end, what happens after all that explanation, all of this internal the plasma heat, the 1/5 of it, and whatever you put in for external heating purposes, comes out through a surface, through these variety of mechanisms. That's the hardest part, by far. It's because that's all limited by your ability to carry away heat through an engineered material. So this means you must have high thermal conductivity, you want the system thin, you must have coolants in close proximity. Okay, that's already a hard problem. And in fact, but wait till you hear how hard this problem really is, because that's actually not the hard problem of it. Here's the hard problem. It's because 4/5 of the energy comes out as the neutron. So from an energy transfer point of view, this is by far the simplest, much simpler. Remember I told you before, because neutrons have because they have no charge. There's other kinds of reactions, but the primary way they lose their energy is elastic collisions with other nuclei, which just means the atoms which are in this thing that you put around. We have a name for this. We call it the blanket, because it literally just surrounds whatever fusion place where the fusion goes on. Because they have such large mean free paths. Oh, and by the way, they're undergoing elastic collisions. So it's rather, you asked about moderation. It's the same way that you calculate moderation in that sense, is that in fission, you're moderating the fusion of the neutrons so that they go back to room temperature so that they can cause the next fission reaction. In fusion, all you're caring about, you just want their kinetic energy. And then their kinetic energy ends up as heat, because what they're doing is they're undergoing elastic collisions in this medium. So almost always this medium has to be in the solid or liquid phase.
Sorry, Dennis, can you plug it into the fission reactor so you have a stream of neutrons and then maybe it would...
Neutrons, yes. It's called a fission-fusion. There is such a thing which has been looked at by many people. It's called a fusion-fission hybrid. The idea there is you use the high energy neutrons So instead of only relying on the internal neutrons which are made by the fission itself, you actually have an external source of the neutrons which come in. So you can think of it as a subcritical pile, that namely, if you take away the neutrons from the fusion, the system goes subcritical, and so it stops using power. We can get back into that. You can use it in
It's
that way.
interesting. It sounds to me reversed on the thermonuclear weapon, where it was like the fission would start fusion. Here it's the fusion effect.
Yes. Yes. So you're right. In a thermonuclear weapon, fission starts, and then it makes an X-ray bath that basically triggers the fusion reactions to make energy gain in the systems. Yes. So you're right. It is like the reverse of that. That you use thermonuclear fusion to actually produce those things. I mean, I can editorialize on that. The problem with it, there's some people who advocate for it, but the way that I look at it is that it adds the complexity of fusion into something which is rather simple, which is basically fission. Fission works. Criticality works, and criticality control work. Otherwise, you wouldn't have fission reactors, right? And then the fusion person looks at it and you go, oh, okay, great. And now what I've just done is I've added in all of the environmental waste and proliferation issues that come with fission to make fusion work. It's just like, ugh. One of my colleagues described it, it combines the worst parts of both.
Is there a...
Which I always felt was
Is there some kind of situation where, for example, you're in space and you can't bring a whole nuclear reactor, so you then bring a small fusion reactor and a small amount of radioactive material and you combine them? So where like some flavor of that, like where you can't, something that's too small to be a nuclear reactor.
Yep, we designed it already. You should come take my class, my fusion design class. So what we designed was a fusion-fission hybrid, for the reason that what we were designing it for was colonizing Mars.
There you go.
Excellent.
So just you don't have to bring as much nuclear material, or the size of the reactor can be smaller, and you can turn it on and off, stuff like that.
So it had two motivations. One was it's unclear about who's going to let you launch things into Earth orbit with a critical nuclear assembly.
SpaceX probably,
pile.
if anyone.
Well, don't get me started on that one. Actually, my class was this class was a bit of taking apart the mythology of going to Mars and colonizing it, which will not happen if you don't sort out a whole bunch of nuclear issues, it turns out. By the way, solar sucks on Mars because it's a lot further away from the sun. And there's no oxygen to burn. What are you doing, right? So you look at those things. So it turns out that there is a fuel on Mars for fission. It's called thorium.
But you have to breed it into uranium.
Bingo. In fact, it's a fertile fuel is what we call this. So if you actually expose it to neutrons, it will produce fissile fuel, and that way you can burn it. And that was the idea that this is why we used, and this approach was you wanted a fusion-fission hybrid because you wanted to be able to breed fuel on the surface of Mars after that. So that, along with the launching things which are subcritical from a safety point of view, seemed to be a winner. There's a whole bunch of other things which come into play like that, like not having everyone die of radiation poisoning on the trip to Mars.
Because you have to shield yourself from the uranium or whatever it is.
No, it's not from that. It's from the cosmic rays. It's from the cosmic background. Yeah. This is irresponsible, actually, for a lot of people. A lot of people who should know better, actually, is that when you look at the radiation exposure that you would get in standard rocketry, it was like there's a reason why we stay in low Earth orbit all the time for all these things. It's for how long? Because once you get into interplanetary space, the problem is twofold. One is solar radiation, which can be very, very extreme, and solar events like coronal mass ejections. And the real big one is the background radiation. So this is like the GeV class protons, which are basically in the background cosmic radiation. Turns out life starts on planets for a reason. It's because, by the way, how do the reason that we have a relatively benign environment is because two things: atmosphere and magnetic field that we have around the Earth, which is itself interesting because I have many colleagues who work on those problems because they're related to it's plasma physics, right? It's charged particles. It's all those other things. So that ended up being actually one of the solutions that we came up with. Was we thought of this, and we haven't really pursued it more since then, but we actually came up with an idea of having the astronauts live inside of a superconducting magnet.
That's pretty cool.
So what it would do is reproduce the dipole field that we have on Earth, except it's about a million times more powerful magnetic field. But if you remember your electromagnetics, you remember the dipole moment has to do with the strength of the magnetic field and the size of the object. So you can actually approximately make the Earth's dipole moment with superconducting magnets and this thing. And so what you do is you have the astronauts living inside the electromagnets, which is like spinning, basically. And this way they have centrifugal force for gravity purposes. And then the charged particles get deflected around the magnet because of the...
So what are those magnets? Is it like some MRI scale magnets?
It's even higher. That's actually why this was an interesting one. It all came from the idea of using the new magnets that were developed for fusion. So these high temperature superconducting magnets, because they can produce higher...
How many Tesla? Wow,
10 Tesla.
That's impressive. I just visited my friend and they combined like the two MRI magnets for confining plasma at UMD. So it was like already pretty intense to stay next to those magnets. I don't know. Oh, the astronauts feel inside those magnets.
Your credit cards get wiped.
No, so actually it's a good question actually, but think about your electromagnetism. If you make a hollow ring and the current is on the outside of the ring, the magnetic field inside gets really small when you live inside the magnet.
Yeah.
So you're living inside the volume of where, because the currents roughly cancel out.
Oh, I see. No currents. Okay.
Is outside.
Yes.
Oh yeah.
So inside is better than outside.
It's not zero on the inside. Yeah. So this is why you basically it's a ring, and then you have the current that produces the superconducting, and the superconductors are on the outside of that, and the current is going like this. So you basically get a toroidal ring. This makes a dipole magnetic field that is super intense on the inside of the ring, but on the in the interior part of the column, it's not zero, but it gets a lot
what
smaller.
happens to all the charged particles inside our body, right? They'll be like the magnetic field would accelerate those processes.
Yeah, it's a good question. Yeah, so it turns out around I think it's about 4 or 5 Tesla, you start to, if you immerse a human being in 4 or 5 Tesla magnetic fields, they start to hallucinate quite badly.
Oh yeah, because we're diamagnetic, I would imagine that would have quite some effect. And at some point you start floating like a frog.
Yes, you start floating. Yeah. Anyway, so you don't do those things. You knock it down to, I can't even remember the number we came. I think we got it down to half a Tesla or something on the inside. That's still pretty high magnetic field, but you're probably okay. It's better than getting all of your DNA screwed up with radiation damage from charged
And you
particles.
can
Anyway, yes.
make a mu metal suit for
Something like that. It's like Magneto or something. Yeah. But back to the neutrons. The neutrons are interesting because as the neutrons come out, their average distance between collisions is like large, 5 to 10 centimeters, and then it's an elastic collision, most of them. And so what this means is they basically do energy transfer, and that's just following kinematics. So of whatever it is. But you asked about moderation, actually. So this is why, like in fission devices, you use water. It's because the neutron is interacting with protons, so it has the most efficient energy transfer, because by classical kinematics, right? When the masses are matched, you get the maximum energy transfer possible with that. And it's at 14 MeV, and you need to get it down to like 0.03 electron volts, which is room temperature. So it's actually going around, it's about 8 to 9 orders of magnitude drop in the kinetic energy. So what this means is that it means multiple collisions, scattering collisions, and then on average, each of the collisions, it loses some fraction of the energy. So it's like a power law. You solve this, and it turns out if you send 14 MeV neutrons into water, it takes them about 30 collisions to slow down to near room temperature. And if it's something that has a worse match for a mass, so like iron, it's like 600 or 700 times it has to collide with things. So what this looks like is it's basically bouncing around in this to thermalize. But of course, every time it bounces on something, it's imparting kinetic energy, but that kinetic energy then is in a charged particle, and so it has a very small range. And so it basically just provides local heating. So it basically, in the end, what it just means is that you get volumetric heating from neutrons, which is fantastic, because volumetric heating is way easier to deal with than surface heating. And in fact, the best solution to this is that you primarily want to make this medium out of a liquid. Because if it's a liquid, then what this means is that the direct volumetric heating is occurring in the thing that you're going to transfer the energy out of. So in the end, that's how you do it, right? You get this volumetric heating and you're pumping a fluid of some kind through it, and then you pump it in and out of the system at a constant rate that exactly matches the total amount of fusion power that you get. So there you go. That's how simple and complicated heat transfer is, but recognize about how nasty it is. One is that it all has to come through one surface, like shit. That's really hard, right? Because geometry is against you, right? Because all heat transfer is surface limited, and you only have one surface. This makes it harder already, right? Because you want high average power, volumetric power, not surface power. But they're linked to each other through the physics of that one. So geometry is harder, and this also means whatever the fluid that you're putting through the system should not interact very strongly with whatever is the containment mechanism that you're using. Like, in one sense, fusion has incredible flexibility because it's the only energy source that where the working fluid, by definition, like the working medium of the engineered system, has nothing to do with the energy source by definition, because they must remain isolated from each other. In other words, the blanket has no idea that there's a thermonuclear fusion plasma inside of it, and the thermonuclear plasma has no idea there's a blanket outside of it. So this is cool, because what it means is you can separate the function of these things in important ways, which you can't do like in fission, for example, because they actually interact with each other. And the same thing like in coal and all these other things, fusion, you can separate them. But this also means that you have to keep them separated. You can't let like the blanket like leak into the plasma or vice versa, because you have to keep them fully isolated from each other. The big one then comes though too, so that part's relatively is important, but you also realize right away the challenge of heat transfer is one of the major problems of thinking about fusion power plants, because it's the rate at which you can safely bring out the energy, which is the thing that sets the economics, because that's what you're selling in the end, right, is an energy. But here's the kicker, right? So in DT fusion, you have to do two more things. So one of them is you have to make tritium. And the reason for that is tritium has a 12.3 year half-life. It's produced in the environment. It decays so fast that there isn't any tritium really around on Earth at all. This means that fusion devices have to be self-sustaining in tritium. What you actually are doing is tritium is incorrectly stated as the fuel of fusion. It is absolutely not the fuel of fusion. It is the extra neutron that you add onto the deuterium is like a catalyst basically in the system. And you're using it, it goes right back to your original question, that extra neutron gives you this much higher reactivity. Just like you think of a catalyst in a chemical reaction, you add it in to increase the reactivity. But you recapture basically that catalyst and use it over and over again. In fusion, the catalyst is the extra neutron. And that neutron now comes out and boom, 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 bounces around, but it turns out it has a fission-like reaction, 1000 barn, with lithium-6. And the neutron actually undergoes a nuclear reaction. It is like a fission reaction, actually, more than a fusion reaction. It undergoes neutron capture into lithium-6 and produces net energy, which is cool. That actually, it's at an energy which is around a quarter of what the whole of fusion energy is. So you actually get more energy out of the system. And it produces a helium particle, surprise, surprise, because that's why it wants to release net energy, because the helium is so stable, and a tritium. And then so what you do is you take that tritium, and then you're going to regain that tritium, which is really the extra neutron, and you put it back into the system again. And you keep reusing it over and over again like that. So in the end, tritium is that. So So what does that mean? Is that so you're already seeing some constraints, right? This means that this medium must contain lithium at some pretty significant fraction, because what you need to sustain this fuel cycle is that for every fusion reaction that occurs, on average, you must produce at least one or more tritons from that reaction to keep this fuel cycle going, because you have to recapture the catalyst to keep it going as well too. So we have an experiment at MIT that is, in fact, you asked about students. That part of the problem, which has largely been, people knew about this challenge, but has largely been ignored. You must have this for fusion power plants. And so we're actually commissioning a small, relatively small experiment, like a garbage can size experiment, that's actually going to breed tritium from neutrons, from 14 MeV neutrons for the first time. Yeah.
Which building is this in? Maybe I'm sitting right on top of it.
It's an It's an NW12.
Oh.
No, 13.
Okay.
13.
Next door.
So it's just across the street. Yeah. So it actually has a small accelerator and has a big, basically has lithium-containing liquid around this. So that's one constraint. So obviously, going back to those two ones, you can see, I was like, oh, well, I want this to be liquid, and I also want it to contain lithium. So it turns out there's lots of liquids that contain lithium.
But this will be like an engineering challenge to purify that tritium back out.
Yes.
On site, probably.
Exactly.
Reinsert.
That's exactly what it is.
That's interesting.
And so it turns out this problem, well, there's nuclear physics involved, but we know a lot about that, and there's a few subtleties in this. The real thing that's hard is the electrochemistry, basically, of the system, because it's producing tritium, and what you would want to do is have a purification and extraction system that actually works really effectively at very low concentrations of this tritium, and that's unclear about how. That's why that's the primary purpose of the experiment, is actually to do those things. And so you can see is that this is like classical nuclear engineering, right? It has nothing to do with the plasma. It's actually chemistry systems. It turns out that there's some interesting things around corrosion and other aspects like this. So there's some material science and engineering that comes into this. And then you put it into an integrated system, but it has nuclear effects going on inside of it. This is why a lot of nuclear engineers are actually chemical engineers that are applying their discipline basically into the nuclear field. That's really exciting because this is an obvious necessary part of fusion. The final one is beautiful because it actually takes full circle all the way back to like why fusion works in the end. It works because of the binding energy of nucleons, right? So if you remember this, I was drawing with my hand, right? The binding energy per nucleon of the different things in the periodic table, and it peaks at iron. But I didn't say what that absolute number is. And that absolute number, about 7.5 MeV per nucleon. What does this mean? Remember what this crazy unit is. Mega electron volt, right? This is a million volt, a single elementary charged particle falling through 1 million volts of energy. It turns out MeV are the natural energy units of nuclei. That is the strong nuclear force. The strong nuclear force is holding nuclei together. And that's actually the strong nuclear forces between the protons and the neutrons to each other, right? But only at distances of nuclei, approximately 10 to the minus 15 meters. It's by far the strongest force of all four of them. Why is this important? Well, it's because at 7.5 MeV per nucleon, this tells you it's basically the binding energy that holds matter together, that holds nuclei together. And if you remember what happened, we're choosing DT fusion because it gives us this whopping big energy gain. It's 17.6 MeV, and 4/5 of the energy goes into the neutron. So it's at 14 MeV. Oh, this is interesting. The projectile that we are making from fusion actually has a higher kinetic energy than the average energy that holds together the nuclei of any nucleus. And by the way, iron's the best and it's only at 7.5 MeV. The other ones are a little bit weaker. Whatever, it doesn't really matter. What it says is that neutrons are very interesting at this energy. And by the way, This is different than fission, because fission produces almost all of it's actually technically a spectrum, but it basically produces almost all of its neutrons around 1 MeV. So it's actually below that threshold. So this is where the fascinating thing of DT fusion or fusion comes in, is that what that means is that that neutron, and it has no Coulomb charge, so it has no energy penalty to pay to enter into a nucleus. So it turns out is that, remember I told you it's the neutron is scattering around and causing collisions. Okay, all very good. But what it can also do is that it can enter into a nucleus and basically rearrange the nucleus because it's got enough free energy in its kinetic energy when it's at 14 MeV. So this is before it slows down. Notice once you start slowing down the neutron, this problem gets to be way less. But you can't avoid the fact that they start at 14 MeV and you must undergo some of these collisions. So there's basically a finite chance that what it's going to do is so-called transmutate the nucleus. And what does that mean? What it wants to do is remake the nucleus based on the rules of nuclear physics. So Mr. Neutron comes in and it just causes havoc with everything because it's got so much free energy. It goes, I can just rearrange the nucleus into a new thing. And in particular, guess what it loves to make? Helium. Because helium has a strong binding, is such a stable nucleus. And like in all these kinds of reactions, it loves to find energy minima, right? So it wants to make helium. And that's exactly what happens. So it turns out for every nucleus above lithium, basically, which is all of them, is that the neutron can make helium from the nuclear physics point of it. And it does this at a finite rate as compared to the other things. It's an alchemy stone.
Exactly. Can we do alchemy? Can we do lead to gold? Because gold
it
has
is,
less.
it is
Neutron alchemy.
79 or something.
Yes, it is alchemy. It is real alchemy, right, around all these things. Now, so we've got the picture about why this is hard. Why is it hard? One is that you're undergoing elastic collisions, which literally are, and by the way, you just do simple kinematics. Remember, we already talked about what holds regular atoms together at a surface. It's order of 10 eV. The same thing happens. It's about 50 eV of like solid matter. If you just do a thought experiment of going in and plucking an atom out of a stable lattice, it takes about 50 to 100 eV of energy because that's the energy well that it's sitting in. It's a 14 MeV particle that's actually undergoing collisions that actually hit those. So it basically disrupts the atomic order. So you go through the calculation, what it turns out is that for solid matter, what's happening is it's disordering the atoms at the atomic level. Like they're literally ending up in a different place. So we call this we actually normalize it to the original density of the particles. We call this displacements per atom. That namely, this is the statistical average of how many times each of the atoms has been taken away from its original lattice location. Would you like to hear the number that this actually, it takes a little longer to calculate, but it's actually not that hard to calculate. It turns out that for a typical like reactor power plant where, remember I said this energy is coming out, and we typically use a unit of thinking about this as 1,000,000 watts per square meter, megawatt per square meter is the power that's coming out through it, because that's typical of what you would get in a nuclear power plant. That will displace every atom in the front part of the surface 10 times. Every single atom will be displaced from it's like, what? That doesn't even make sense. Because once you reach 1, doesn't the material just fall apart because you've displaced every single atom? It turns out no, because it's so the neutrons are like a forge in a way at the atomic level for the material, because what it's doing is that these atoms move around, but then they want to fall back into some local equilibrium in the end. But you're forging in this material at the atomic level. It's like, okay, wow. Then you add on top of it, and on top of this is that with also some fixed probability that instead of knocking it around on that, it actually literally remakes the nucleus. Like it turns into a different element.
It's a defect.
That's absolutely crazy. Yeah.
So you're producing some kind of foam with some helium and some random impurities and
that is
lots
very
of
cool.
vacancies and so on.
No, you change the isotopes, right? So what this means is that fusion gives you this extraordinary physics flexibility, because it comes from the physics of fusion, of designing this blanket in an almost arbitrary way, right? But then the other parts of this, you just go, holy cow. It's like no engineered system like we've ever, like even in fission, where there are things that get altered by the nuclear environment and so forth, it's not even close. In fact, it's interesting. It's because fusion sits on one side of the energy threshold as compared to fission. The experience from fission is essentially useless, really, for us. And what we have in front of us is a coupled engineering and physics design challenge, which tells you, in fact, there's no such thing as a material, because the nuclear physics doesn't work. There's no such thing as a material that's tolerant or resistant to change in this environment, because it wants to remake the nuclei, right? And it wants to disorder them by the basic processes which are occurring. And so this is such a cool science problem, right? People go, when are you going to have neutron-tolerant materials? Never is the answer, because you can't make them from the rules of nuclear physics. But what you can think about are holistic systems which actually adapt to what's going on and in fact find new equilibrium which are occurring. So for example, this is in fact what came out of my design class, and in fact why we concentrate, and this is what Commonwealth is using and others are using, avoid solid materials. Because solid materials are what care about ordering of atoms. Liquids don't, right? And liquids, by definition, can be used for energy transfer because you pump them in and out of the system. And as you pump them in and out of the system, what if you actually alter the liquid features, right? You actually replace atoms, or you remove tritium, or whatever it might be. Oh, yeah. So conceptually, you see, that's a much better way to do it. But you can't avoid all solid materials is the problem. So in the end, we're going to have to come up with systems that actually adapt and understand. The way I look at it is almost like go with the flow, right? That almost like an engineered system. And you can also see why material science is so important in fusion, is that you can think about a material that actually finds new equilibria because it's being so perturbed, but it actually maintains its engineering functionality, is going to be one of the greatest conceptual and intellectual challenges of making fusion economic.
Are there any recent advances in material science that directly found their way into fusion science? For instance, graphene has been very studied and successful elsewhere.
Yeah, so graphene has come in through other means. Graphene itself doesn't really fit the bill, and it's because of this disordering business, right? Graphene works in general carbon systems because of the atomic ordering. So it's interesting. In fact, I worked a lot in graphite systems and so forth because they're excellent in many ways in a nuclear environment, but they suck from that point of view because they get so quickly disordered. So for example, if you take things like high density graphite materials and silicon carbide is a little bit different actually, but graphitic materials that have very high thermal conductivity, which is very good. They're tolerant in lots of other ways, that they will their thermal conductivity will drop by a factor of 100 at fractions of a displacement per atom. So this would happen like in a day or two in a fusion device. It's like, oh shoot. Yeah, but there are things which are coming from a variety of ones. For example, high entropy alloys are an interesting one which are emerging, that namely in the end, that's actually what the system is doing, right? Is that it's actually increasing the entropy in the material. So you actually start with high entropy so that it's already it's closer to its like final state. And so the relative impact of the neutrons of the displacements can be less. So those are ones which are coming. I think the really exciting frontier is the combination of rapid materials fabrication and assaying that are coming from automated techniques, and a lot of this is coming out of the material science community and my colleagues that work on this, that sit at that intersection, like our ability to go through like millions of permutations of different kinds of alloys, for example. In fact, I've got right now a PhD student who's doing that both experimentally and, of course, computationally. That's the other part where the blend of advanced and more rapid prototyping techniques combined with high performance computing are really at the frontier of what we do. This is the other one, along with and in fact, there's an experiment coming at MIT that's actually itself going to be going directly after these issues. We're actually going to have a new facility that's going to be right across the street from you. It's actually going to be an NW21. Oh, yeah,
The
NW21.
Nabisco, Nabisco lab, yeah.
Yep. So it's the place where the fusion experiment was in the large concrete bunker, which is there. And we're going to install a very high energy cyclotron to rapidly damage and transmutate materials.
What are the materials that you want to transmutate from and into?
There's some basic requirements in this, like you almost always start with alloys or some kind, or elements that have high thermal conductivity, because if they don't have that, you're toast already for the first wall materials because of this heat conduction problem. So you tend to start, and the other thing is that you don't actually want to, this is one of the other features of fusion, is that in the end what you're making is helium, so it has no radiological consequences. But if you put bad selections of isotopes in front of the neutrons, you'll actually make radioactive isotopes that could have features so that you would have to store them for a long time. We don't want to do that, right? That's one of the great features of fusion. We can design the so-called activation profile and the waste product profile of this by through cleverness. So we tend to pick things which we call our low activation. So these are isotopes like vanadium, for example, which are have a very mild one. Anything that's low atomic number, like silicon carbide, is outstanding on this. That's a really good one. But the actual answer is we don't really know. And here's one of the, if there's students watching this and you think about the frontier of this for fusion, is that it's also about what it means about its possible impediment actually in fusion. Is that approximately right now we have about maybe a day. If we actually built the fusion power plant and are operating it, the materials directly surrounding the device, our ability to predict about what their fundamental properties are, like thermal conductivity and strength and so forth, maybe a day of operation. And you want these to operate for a year. And the reason for that is because there's never been a working fusion power plant. So we have no empirical direct evidence. And there have been a few things that have come out of fission reactors, but even those are extremely limited about what they tell us, because the physics is different about what that is. Wow. And so one of the interesting parts of fusion is that it's clear we're going to have to use the first fusion devices to actually give us some of the answers about that. But then the other part is, let's be really, really clever about down selecting choices through things like rapid assaying and computational modeling to actually get us to a point where our guesses are better earlier on. And I think this is clearly one of the intellectual frontiers of fusion, which, by the way, will be really amazing because it's going to push material science, production, testing, modeling to its absolute limit, which is the other cool part of fusion, right?
It's extremely fascinating.
It tends to be right on the frontier of what you can figure out, yeah. Right on. But it's not impossible. We know it's not, and in many ways, it just has to get good enough that we know that we can use it in the system, because by definition, you're going to have to replace these components with some frequency. So what you just don't want to know is that it's unknown, right? About how it's going to react. We actually hope that facility is working by the end of next calendar year at MIT, and that will be a frontier science capability. Yeah. Yeah. And it's a cool science idea, by the way, which also I came up with about 12 years ago in an undergraduate design class with a few material science people, and it was basically like, how do we get to what's a tool that we could use to start rapidly but correctly damaging materials in a way that a fusion device would? And the answer was protons, which is very non-intuitive, but it's a cool physics idea that, namely, if you get protons to be energetic enough, then they'll enter into the nucleus, and because what really matters is the strong nuclear force, which doesn't really care that much about protons or neutrons, because both participate in the strong nuclear force. You just need to get the protons energetic enough that they can actually enter into the nuclei, and then they'll start doing all the same crazy stuff that neutrons do. And that turns out to be around 30 MeV, like about double, basically, where the neutron starts. And it turns out high energy compact cyclotrons, which are coming out for medical reasons,
Yeah.
medical treatments, things like that, fit the bill. And it fits into our cell at MIT. We've just garnered some very generous donations, and we're going to install that, and we're going to start discovering. It's going to be cool. I think there's going to be a pool on this about which materials will fail the fastest
Yes.
in the environment. But the way I look at it, it's easy. But I'd rather know now than having to put it and having it fail in the first fusion devices. And what's interesting in this is that it serves not just a tokamak, it serves anything that's going to do about fusion, because they all face this challenge.
Yeah, it sounds a little bit reminiscent of when Edison was trying out different filament materials to see which one would last the longest. You just have fancier materials.
That is a great compliment, and hopefully we do it. So empirical exploring is always important in this, and having the right tools. And in fact, that's the other thing that's cool this proton facility does. It actually accelerates the damage by about a factor of 10 as compared to what you would actually get in a fusion device. So when you put that in for a day, it's like having it in there for 10 days in a fusion device. And as I said, that already takes you outside of where our present database is. So rapid assaying, trying, we're going to have to do things empirically, but I hope in a way that's even smarter than that. Because you just can't do it through pure empiricism, because there's too many combinations of, like, in fact, that's one of our PhD students right now. He's looking at just one, it's a tri-alloy that involves vanadium, and there's something like 10 to the 14 permutations of the alloy. You're not going to do those empirically,
Yeah,
right?
so you need this dynamic design of experiment that keeps adapting. So you use AI in assisting the design.
Yes. Yeah. The beautiful symmetry of AI with fusion is that we both probably need each other. You know?
Right. Because it's very energy hungry.
Yeah, so that's what my question on about your Commonwealth Fusion project. So how viable the coming generation of the fusion power plants, because we know there is a high demand for powering the data centers and tons of video cards.
I think maybe the one thing we haven't discussed, which probably is really important to touch on, is just going back a little bit, the tokamak, just like roughly explaining the tokamak, and then what happened with ITER, and then the insight about having a high magnetic field opening up the path to an actual practical power plant. I think would be a disaster if we didn't cover this. So I just want to, before we go into get lost in AI, I want to make sure we can come back to it, I think. Let's go back a little bit to the history of the tokamak, or like how, just roughly how it works, where it came from, and then what happened with ITER. Basically, how did ITER turn out to be what it is? How did they decide on the design of ITER? And basically, where did the insight come from that like the new high temperature superconductors opened up this new path to commercialization? I think that storyline is very important context for anyone who hasn't heard it.
Yeah, sure. So let's go to magnetic. What this is magnetic confinement, right? So in magnetic confinement, it's the Lorentz force. It's the force which is exerted on a charged particle when it has a magnetic field. The Lorentz force is the product of the charge of the particle, which in our case is fixed because they're the hydrogenic charges in the electron, the velocity of the particle, and the strength of the magnetic field. And it is the force is V cross, so it's a cross product force, right? So it's the velocity of the charged particle crossed with the magnetic field. So those two are vectors, obviously, right? And so it's a cross product, so this means that the force is always perpendicular to both the velocity of the charged particle and the magnetic field. Right, you can start using your right-hand rule to figure out which one those are. The fusion has to happen in the plasma state because of the necessary temperature, so we always talk about plasma, so that we'll just assume it's a plasma. And a plasma is a collection of an equal number of negatively and positively charged particles, because that is dominated by Coulomb collisions. That's the or where its behavior is dominated by collective Coulomb collisions, which just means that within I just have to define these because it's important, that within the Debye sphere, which is basically, or the Debye length, that is the distance over which particles can feel the effective Coulomb force of other charged particles. And outside that, they can't, because of the self-shielding that comes from the rearrangement of the nuclei of the electrons. that basically want to shield out the effect. That's the other effect that plasmas have, is they are dielectric. So that you talked about diamagnetic, so they're dielectric, that namely the electrons always want to react in a way that actually shields out the application of external potentials, including the potential or electric fields, including the electric field of the particles themselves. That's the nature of the device here. So basically in the end, a plasma has, at minimum, has many hundreds of particles in the Debye sphere. In a fusion device, if you think for magnetic fusion, the Debye number is something like 100 million. That's actually, by the way, why from a fundamental science point of view, why plasma confinement and so forth is such a weird discipline. That normally, in the end, plasmas are literally just the Lorentz force and the Coulomb force. That's it. That's all that's happening in it. But you can't solve it because it's a 100 million body problem. You can't solve it from first principles. So anyway, in the end, that means we have a plasma. And remember, we need containment. We need isolation of it. What we use is the Lorentz force. So you immerse the plasma in a magnetic field produced by external electromagnets. And the nature of the containment is that the particles will execute circular orbits around the magnetic field because the force is always perpendicular to the direction of the magnetic field and of the particles. This leads to cyclic motion, right? The frequency at which that gyrates at is only set by the charge of the particles, which again is fixed in magnetic fusion. The mass of the charged particles is also fixed in magnetic fusion, and then the strength of the magnetic field. So that's the gyro motion. And then if you calculate the equilibrium of this means also that the particle is executing an orbit of a particular size called a Larmor radius or a gyro orbit, right? And it's basically the ratio between the velocity of the particle perpendicular to the magnetic field divided by the cyclotron frequency. And so what that ends up being is that it only depends on the charge, the velocity of the particle, the strength of the magnetic field, and its mass. And again, remember, a whole bunch of those are fixed. Why is this in magnetic fusion? This means is that this circular orbit, this gyro radius, is the fundamental unit of confinement. And it's because if you make that is the physical size at which this particle wants to stay isolated away because it just wants to keep going on that circle. But there's no force by definition parallel to the magnetic field. So this is problematic because this means that there is no confinement along the magnetic field. So what you do is you find an axisymmetric magnetic field, that namely you wrap the magnetic field back around on itself. So there's a whole variety of configurations that do that, and the tokamak is the simplest and so far the most successful one of those. So what it makes is it's a set of electromagnets that produce a toroidal, which just means in the toroidal geometry of magnetic fields that close back on themselves, so that in the end, in this soup of the plasma, the particles have no choice. They have to execute these gyro orbits around on it. That is the nature of the confinement mechanism in all magnetic confinement. And so what's an interesting part of this is that it goes back to the Lawson criterion, which knows nothing about magnetic fields or anything. It's just the nuclear condition of energy, power balance, basically, in the system. And what the Lawson criterion tells you is that the two parameters are basically the plasma, the temperature of the plasma is an independent parameter as compared to the other features, basically the density and energy confinement time of this. And when you draw the Lawson criterion, you get curves that actually have minima in it, that namely what is minimum. So this is the height of the curve is basically how dense or confined the plasma must be versus the temperature. And this actually has a minimum. And that minimum occurs around 15 keV, which is about 150 million degrees Celsius. So basically, as a fusion designer, you always design the plasma to be near that temperature because it's going to require the minimum and density of the fuel energy confinement to achieve high gain. Why does this all matter? And basically what it says is that the temperature of the plasma fuel is not really a variable very strongly. Although it varies itself, when you design it, you pretty much always design almost exactly the same temperature. And why does this matter to this? Well, because the temperature sets the average kinetic energy or velocity of the particles, which sets the size of the gyro orbit. So if you take 15 keV, that gives you an average perpendicular velocity. And so it turns out that number is fixed. It only changes like the square root of the velocity, of the energy anyway. What happens is that the size of that gyro orbit is only set by one thing, the magnetic field. That's it. Because all the other parameters are more or less fixed in it. And it scales inversely like the size of the magnetic field and linearly, right? So that's the nature. So why is this the nature of the confinement? Well, it's because in the simplest form, then what's happening is that the charged particles are executing these circular orbits, right? But remember, I already told you before, is that the nature of the of all these systems, there's many more momentum exchanging collisions going on than there are fusion reactions. Fusion reactions are rare, actually, in the system. It's just that they release a lot of energy. So what's happening is these particles are constantly scattering off of each other. But what happens when you scatter off of each other? Oh, well, conservation of momentum actually allows, this means two charged particles bouncing around like that, they can actually, it's a cartoon because it doesn't actually happen like that. It happens because of collective Coulomb collision effects. But they're basically spinning around like that. But if they undergo a momentum exchanging effective collision, this means they can get bounced onto another gyro orbit. If you think about magnetic confinement as basically being the magnetic field being my fingers, then the particles are executing orbits around this one and around the next one like that. But once in a while, they actually collide with each other and skip over to one of the next ones like that. And what you're doing in the end is you build a physical object that has a certain number of these gyro orbits encased in it. We have a special name for this. We call this rho star, because rho is the symbol that we give to the gyro radius. And what we do is we divide this by the linear size of the device. Why does this matter? It's because, do you recognize this problem? It's a random walk problem. It's a diffusion problem of the confinement means, because remember, in fusion, the energy is in the particles itself, right? So energy confinement is the rate at basically which these scattering collisions want this to leak out down the energy and temperature gradients onto the outside, and that will be set by how those things happen. There's other things which are occurring, but that's the basic process that occurs in this. This is the nature of the confinement, and then is basically something like the normalized number of radii compared to the physical system, and it's a diffusion problem, so it goes like the square of that. Because you think of any diffusive process, right? So it's the number, so how long it takes to leak out goes like the square of the number of steps that it has to make. And that's basically what's happening. Now, that skipped a whole bunch of underlying theory and all that, but that's the basic physical concept. So in terms of confinement, what this says is that what I want to do is that I've got two ways to solve it, because that's the fundamental nature of the confinement. And in fact, we've done many, many experiments that show this is exactly how it works, right? Is that it's sticking these number in. So what I want to do is make the size of that gyro orbit really small, because then that means is that the normalized radius then to this is actually can shrink as well too. But the object I'm building is three-dimensional. Oh, wow. Oh, yes. So if I have to get the normalized amount of this down to that size, and the only thing that sets it is the magnetic field, increasing the magnetic field should improve the confinement by the square of that, but then the volume of the object that you're building scales like the cube of that. So it's b to the 6th power. It's like, oh, well, why is that important? It's because that's what fusion is. Fusion's economics is really simple in some sense. It's like you're going to spend a lot of money building this complicated contraption of magnets and all of these things. And that's all the money you're going to have to borrow money. You're going to build this thing. And then because the fuel is free and everywhere, that's not really, there's a few subtleties to it, like how fast you have to replace the materials. But the real key challenge is you need to make an inexpensive object at the beginning that actually meets the physics requirements of the confinement. So being able to increase magnetic field approximately changes that b to the 6th power. Now it turns out it's actually not quite as good as that, because there's some subtlety effects that actually, subtleties of effects that come in through confinement, but that's not too far off. The other way to think of it is that, because the other part of what's going on, that's the confinement part, right? But there's another part, which is...
We can also, maybe for a point of acceleration, since the distances are smaller, maybe it's also the way to accelerate plasma, going into smaller scales instead of larger ones.
So you can't, right, so you can't use material engineering of any kind in the system because it has to be at high temperature. There are no engineered objects allowed anywhere. It can only be
Well, no, I think a better question is just how small can the tokamak get? Can it be 1 micron? Like, can you make like a tiny nano tokamak basically, or a nano confined plasma?
Yes. On paper, all it counts is the size. So in fact, you can intuit this almost, right? Is that in the end, because the circle is the nature of the confinement, you just have to fit a lot of these circles inside of it. So if you can arbitrarily increase the magnetic field, you can arbitrarily decrease that. The other violation that occurs, you recognize, is that the size of that gyro orbit cannot be a substantial fraction of the physical size, because otherwise the particles will actually be leaving the system. Right, so it's got to be small compared to that. Theoretically, what that says is if you could just increase magnetic fields higher and higher and higher, then you can make the object shrink and shrink and shrink like that to the plasma, of the plasma. Except, it turns out...
The materials will explode or something from the magnetic
room temperature superconductors would be brilliant to have for this, yeah.
Well, actually, but there's a limit actually to it, which is... So one of them is what you just said, is that there is... I'll get back to that. Actually, what happens is that it's actually extracting the energy that can become more difficult if it's... But in generally, actually, it doesn't. Because actually what you're doing when you're shrinking the device, you're actually increasing the surface to volume ratio, which is good, actually.
Oh, but my question was, like, if you have a very high B field, it might start breaking the materials.
Oh, no, it will. So I'll get to that about what the limitations are. But the actual real limitation is there's a de minimis size that actually doesn't come from any of those effects. We already talked about it. It's Mr. Neutron. So the neutron, because it has to undergo many tens of collisions to be able to slow down, and has mean free paths, which are like 5 to 10 centimeters, it turns out when you go through the math of that, it turns out the minimum, the thickness of the blanket is somewhere an order of a meter. The plasma must be inside the blanket by definition, and then the blanket's purpose is to stop all the fusion. And whatever you're using for containment must be on the outside of the blanket by definition, because you're protecting it and you need to recapture all the energy. So at some point, just arbitrarily increasing the magnetic field does not start shrinking the size of it. In fact, this was, you talk about the impact of students, is that this was the origins of ARC and what Commonwealth fusion systems are doing. Is I walked into the classroom one day for my fusion design class, and through it was the high temperature superconductors, because I knew that wasn't, I kind of roughly knew what that was going to mean to the size of the fusion device. But what I didn't know was what the actual physical system, how small it could get. And that was my challenge to the students. We're going to use this, and we're going to make a tokamak as small as possible that actually achieves these particular sets of conditions. And that turns out to be ARC, which is basically the prototype fusion power plant that Commonwealth is still pursuing. But basically others can use the same concepts around on that as well too. So that was one of the reasons why the size decreases with aspect of magnetic field. The other simple one, it's actually really important to the fusion power economics, is that the other way to think of magnetic confinement is, in the end, you've got a plasma that has a particular pressure, which is set by the product of the density and the temperature of the plasma. And that, and by definition, it's out of equilibrium with what's around it. So it's trying to push out, basically, out into the surrounding medium, right? In a star, this is being balanced by the gravitational force, because that's why it's in equilibrium, because the center of the sun is at way higher pressure and temperature, particularly temperature, than the outside, which is very cold. And that's actually why it can't escape, is just gravity. So in this case, you need a balancing force against that. It's the magnetostatic force. And the magnetostatic force, which is actually a pressure, it scales like B squared. Right, so that's the electrostatic scales like E squared, magnetostatic pressure scales like B squared. So this is literally like a pressure which is being applied against the outward pressure of the plasma. And it turns out that for stability purposes, it's the ratio of the plasma to the stabilizing pressure produced by the external magnetic field is a parameter called beta, which is a dimensionless parameter because it's just the ratio of these two pressures. If that gets too high, then the plasma bottle will break, basically, and it will cause instability. And then it turns out by a coincidence of nuclear physics, is that it turns out that remember I told you these things about why we use DT fusion and has a really high reaction rate. It turns out that reaction rate scales like temperature squared in the conditions where we care about for the Lawson criterion. And because it's a binary process, the amount of fusion reactivity that you get scales exactly like density squared as well too. So it turns out fusion power reactivity scales like density squared and temperature squared, which is pressure squared. And it follows almost exactly that. Again, it's a little bit of a coincidence that it follows like the temperature squared, but close enough. The fusion power per unit volume scales like thermal pressure of the plasma squared, but the stability goes like the ratio of the plasma pressure to the magnetostatic pressure, which scales like the magnetic field squared. So at a fixed relative amount of stability, this means the fusion power density scales like the square of the square. So it goes like the magnetic field to the fourth power.
So for all of these things, having a strong magnetic field really matters in terms of scaling. And did you at some point then feel like that is something that is easier to scale and pursue in the private sector with funding from the private sector rather than with government grants? And if so, why and when did this shift in approach come?
Yeah, so I think it was a natural, although it happened for an interesting set of circumstances. To go back to that, it comes to the arguments about why you want magnetic field come from science reasons, right? But they also have enormous programmatic reasons, right? And the reasons for this is that it goes to this business of the volume of the thing that you have to build. It's going to cost you money. This counts even when it's a science project, like ITER. ITER is not an energy project. ITER is a science project. So the cost of these objects is getting larger and larger, and therefore the political and complexities and the realities of how you would fund such a project got also more and more complicated. So ITER required like an international treaty, basically, to get it together, and it required in-kind contributions from large. Why? Because it's a $50 billion class project. And at a science level, that's really difficult, right? By the way, also interesting, very hard to get students involved because it's too big almost, right? Around on those things. That was a programmatic reason about going small. But this business, it's interesting because still many of my colleagues go, oh, see, a weakness of your approach is that the fusion power density goes up. That's bad because it's going to be harder to extract the power. And that's exactly how a scientist views fusion. But when you're a power engineer or an economist, you go, of course you want that. Because it's in the end, the economic gain is the power that you're producing, and the cost is the volume. And so what you're doing when you're increasing fusion power density, which is basically fusion power per unit volume, the inverse of this is basically dollars per watt, because it tells you about how much you're costing to build this object compared to how much you can gain back economically. That is actually the answer. There's two answers, the way I looked at it, and they both served each other. As a fusion scientist, I was incredibly frustrated with the slow pace. ITER is in its 20th year of construction, and it's still not going to be operational for another 10 years. The lack of, and ITER's mission is to get the high gain, and that's the self-determined system. We all agree this is like the critical next step, right? But it was just way too slow, and it came about because guess what? It used superconducting magnets that can only access magnetic field of a particular strength. And when you work through all the details of this, you ended up with a $50 billion size device, right? So when we work through this, we go, oh, if we can access, because it turns out then the answer about the volume, mathematically it's interesting, turns out to be exactly between b to the fourth and b to the sixth. So it turns out to be about b to the fifth power. And the cost of the object, actually, the cost and the volume of the object will scale inversely like b to the fifth. So we said, if we can double the magnetic field and use exactly the same physical concepts that ITER has in it, which have been vetted up and down like you cannot believe. In fact, that's what I worked on a lot of my career, is that it's b to 2, it's like 32. And it turns out there's a little bit of a subtlety that changes it a little bit, but it's close enough to that. We can do something that does ITER's science mission at 1/40th the volume and 1/40th the cost. And we think that will also take about 3 or 4 years to build, not 40 years to build. Because guess what? We'd already built objects like that, right? So you have to add in this. So that was one of the reasons of the motivation to say, let's speed up the science. And I see that as the thing that we do as scientists, to say we need new tools to be able to access new regimes. And that's actually what Spark is. So that's Spark, right? But Spark is interesting. It's not a commercial device itself. So why start a company? Like, why not just go do this in a government way? It's because the reason that you're doing it, the reason that you're building Spark, while yes, as a scientist, it's going to be great, we're going to advance fusion science. The reason that you're building it is to build confidence and building these magnets that actually extrapolate to build economic fusion power. And so it's not going to be a government lab or a government program that builds commercial fusion power. It's going to be a company. And this looked like it was close enough to say, we think because we can shrink the timescale down to like decadal rather than multi-decadal, we can finance this. And the real key thing is having an entity, not a government lab, not a university. You have an entity whose mission is to build an energy product. That's why you do it that way. And there were other complexities around in it as well too, that we were told, because part of it was we tried to get this funded through government programs, and we were told it was too disruptive to what was going on, because we had this very delicate, and remains a delicate, political balance and a commitment to ITER. We wouldn't be able to garner the political support to go down a different pathway, even though it's identical science. So in the end, and it was interesting, it was almost the primary ideas and motivations of this came out of me interacting with postdocs and students. Because the other part that came out was that in the, honestly, what had become a stagnated government program, where even the science was getting stagnated, there just wasn't an appetite to also then do something which is also really important, which is have the risk appetite of actually trying something new. Like going down this path, we were pretty sure the science of it worked. It was very not obvious that the technology would work, because it was going to be a race towards seeing about whether or not could you actually build the team? It's not just about the risk of the science of it. It's, could you build the team? Could you get actually the right kinds of funding sources actually for this? And can you do it on a time scale that you'd be able to meet the demands of the private sector? And we thought the answer of that was yes. And we estimated that, we said, if we can get about order of $100 to $200 million, and we use alongside the company a place like MIT's Plasma Science and Fusion Center and the Magnet Lab, you know the size of it, right? It's like 3/4 of a city block,
Yes.
right? This is not a typical university lab, and a team, and a dedicated team of engineers and scientists working alongside of a startup company. Then what we could do is we could have a crack at actually taking this new material and showing that it would work at the right kinds of magnetic fields for fusion to actually exercise this. So before you went to build a fusion power plant or do those other things, make the technology work in an integrated way. And that's exactly what we did. And we did that in 3 years. We did that in 3 years in many ways because it was funded by a company and because it came from private sector investment. They were okay with us making mistakes and spending money as long as we kept going fast and we kept making improvements in what we did. And in the end, it worked.
Yeah, because 3 years is very impressive for this. It's extremely fast.
And that it was interesting touch point in this. We actually brought this up in front of, for example, a National Academies panel that had experts in magnets, right? And those, how long will it take you to actually get to a thing? They estimated 15 years.
Oh, so there's a lesson to take for, yeah.
And it's because they admitted, they say, we would never have done it the way that you did it. Like, we took risks with this, I mean, not physical risks, we kept everybody safe with it. You know what I mean? We took science and technology risks. In fact, it was interesting. We took so many risks, we actually ended up with two completely different pathways to solving the problems that were involved in this. And that was what was spurred on by, in many ways, the finite timeline, the compulsion towards realizing this wasn't just about delivering on new science. It was actually about delivering to a new idea about how you'd be able to build electromagnets that scaled to actually commercial relevance. So in the end, not only did we, all those papers, I sent you some of them, not only did we, in the end it was interesting. It was this wild combination of, because it wasn't just like, we're just going to build things fast. We actually reinvented, in many ways, the basic concepts about how you would do electromagnets in the superconducting state. And the motivation was that it had to work in a commercial unit in the end. So even though we weren't designing the commercial unit, because we were doing it in an academic setting, that pressure that came from understanding, we're not going to build one of these, we want to build 10,000 of these, meant that we actually had to innovate in a whole variety of ways, including in the underlying physics, about thinking about what it would look like. So in fact, the way that we fabricate these superconducting magnets is completely different than what was considered before. In fact, it was interesting, we had a vote, by the way, inside of our team, and then it was myself as the director and the CEO of the company, we made the final decision. But all of the experienced magnet engineers voted the opposite of what we chose.
Right.
Because we actually chose a pathway that said, we're going to use this pathway because it scales to so much more effective manufacturing.
That's super fascinating. It's so different from how academic research works. Yeah.
But the interesting part of it, but the academic part of it was necessary. Because why was that? Because you needed a deep, deep bench about expertise in superconducting, electromagnetism, material stresses. I mean, all the complexities of how you actually put this together. Like a startup on its own would have had a really hard time lifting all of that. And that's what I see is, I hope there's more of this, is that namely what I would say is that this is a chance I think that we have on the academic and on the university side to realize our level of impact can be higher if we actually break down, but break down the motivation and the ideas about what we're working towards, about how we fund them, and how we organize teams around these different parts. And seeing academia and startup as separate things is actually a very too limiting of a factor, I believe. And of course, startups all come out of universities because that's what we do. Our job is to push the frontiers of knowledge and ideas. But why don't we also think about it as pushing the frontiers of the ideas of the organizations and the things that we build? Because the way we did our thing was we worked alongside of a company that innovated on things that were not going to necessarily matter directly as an academic part of it, but will have a huge impact in the real world. And isn't that what we want around on those things? So to me, it's the thing I'm the most proud of what we did. My little joke is that we were almost like an academic startup. But you take a team like that and apply it and do those things, it will evolve into an amazing thing. By the way, the other part, which was so key to this, is tech transfer. Because when you work alongside each other like that, and it wasn't always easy, by the way, like the tensions that came about from the timelines and the budget, whatever it might be, and just even the mentality that came from the people that worked in the startup company alongside the academic, didn't mean that it was always like a uniformity of opinions. But in many ways, I think in retrospect, it was that tension itself which actually was part of what made us innovate more around on the things. And then but with all of these and the papers and the patents and all that, you know what the thing I'm the most proud of? There was a commercial factory in Devens, Massachusetts, making these magnets within a year of when we actually demonstrated and that was because we innovated in the tech transfer part of this, because it was exactly the same. It was In fact, I was literally just on, because I'm checking in on some of their tests that they're doing right now on a sort of a side basis. And it's literally that I know many of those people at the company trained alongside the MIT scientists about being able to do that. That's why that works. It's like, oh, we should be taking all kinds of tough tech problems and trying to apply kinds of ideas like this.
This is actually so fascinating, and I think a whole topic on its own. So I'm wondering if maybe we could even do a second podcast on just
I
like
am so
funding
passionate
structure.
about this. I am so
Yeah, and we are all kind of in that
it,
same
Definitely.
situation. Like Mike
yeah,
is in a startup,
and
Misha was both a research scientist at MIT and a startup.
you know, right, you know the challenges, and actually what this requires is adaptation. This is, I think we're at a pivotal moment, particularly at US leading research universities. We're actually in a historic moment of change, and a lot of people don't quite realize it. And what that means is that the period after World War II and the normalized amounts of funding and basically the social contract that scientists had was different because it was flush with money. It was understood that this was critical to national security and national economic gain. And we basically built institutions like MIT, and which actually had completely changed what they look like because post World War II, right? And the Bush Doctrine, right? And all of those things.
Cold War conditions.
Cold War conditions, and guess what? It's all evolving under our feet. It's like in a few years, the federal government will not be the majority sponsor of research at MIT anymore. All right, it comes through foundations, it comes from companies, and we should realize we have a structure which actually we should be questioning everything about the structure of what we have inside of a modern research university, because people mistake this about that as, oh, the funding sources are different. What we'll do is we'll just change a few of the rules about how we think of that. No. It's because you should be thinking about this as a different social contract about what we are doing and why we're doing it and who we're doing it with. And I think there's going to be a set of winners and there's going to be a set of losers, just like there was after the last revolution. This happened, which was basically it's a good question. Look, we're local at MIT. Like, why is MIT most usually voted the #1 research university in the world? You know why? Because it invented the modern research university. Vannevar Bush invented it. Right? About these things. But now we can see the problems actually of trying to fit the square peg in the round hole. We have structures around, and even there, like entrepreneur, everyone goes, MIT is so successful at entrepreneurship. You know how much more successful we could be if in fact we figured out how to solve this problem of people and technology and expertise floating across these boundaries that we have made for, in my opinion, a lot of artificial reasons, actually, around on this. And it's like, you guys did a startup at MIT. How fun was it, like, trying to fit TLO into a model that was just like, right? And in many ways, it's not the problem. It's not the problem of TLO or even the people inside of it. The problem is they're working with an outdated model that it actually is incorrect of thinking about how this could actually look like. In fact, I argue the entire value proposition of technology licensing is outdated and incorrect at universities. And we should adapt those things and change them, like we have changed before as well too.
I would actually love to hear a lot more about that in depth.
Yeah.
I feel like we can have this first one, which is more centered on the technology and the physics challenges. And I would love to actually have a separate one where we talk more about the institutions, the funding structures. Yes, that would be, I think there's so much material. Yes.
Yeah, and for that one, this is one of my great motivations about doing some things outside of MIT. So I commented as to one of the startups that we have. A part of that is actually pushing at this from the private sector.
Right.
And I've got some very convincing allies.
Oh, we would be so interested to hear about that, because Mike is also active in that space where he would like to see Change from the commercial side himself, and us from the university
And,
side.
and every young person, every young, talented young people like you who actually recognize, the way I see this from is a very simple way. You use your talents in these systems. Like, you could go work in other things which are not around in this. Like, what you are motivated for doing these things, for making a difference in the real world. Every young student, every young faculty member and student I work with at MIT sees that as their mission. And you work like crazy to do those things. Yeah, and there's some nice things, like we get good jobs and stuff, but you do it because it fulfills two passions. One, you're doing something that is scientific, satisfies your intellectual curiosity, and two, you're doing something that you know is important, right? We need to have a structure which actually feeds that. Otherwise, we can break the system. There's no guarantee that this keeps going like this, by the way. And I hear a lot of people who want to leave the system because they can't satisfy both of those. And that scares the shit out of me, actually.
Yes,
Because that's when the
exactly.
system really breaks.
Yes, and we are at the stage where this is actually a relevant question for people in our stage of our careers. That's exactly a very relevant
Absolutely.
question.
Yeah, yeah. It's interesting, by the way, there's other things going on at universities. You can see it's almost like we're stumbling around trying to find ourselves. It was interesting. Brown University sold something. It had a piece of, or they donated it back to the local Native American tribe that had historic connections with that piece of land or something. So it was about that. It was a nice story. They did that. And it was in Boston.com, and it went down, and below it were like people get to leave comments. So whoever reads Boston.com, not particularly conservative or liberal, whatever, it's just like this cross section of the New England population. Some 60 or 70% of them, the vitriol that was commented to Brown and to universities was, I couldn't believe it. This was just like, oh, it's a university just being woke again. Why don't they give back all we should close these places down. They're just ideological something. Like, I couldn't believe it. Was like this weird.
People think, yes.
This is what people think about what we're doing? No. What we are doing is we are the engines of economic prosperity.
Yes.
That we're the seed parts of economic prosperity and economic dominance of this particular political system. And if we have people thinking like that's what we're doing, we are in real trouble.
There's a very severe problem. Absolutely, yes.
And I think we are to, part of it is that we've lost our way a little bit around on this. And part of it is finding our way in this new era. We have to do this, right? Otherwise, we're going to lose our relevance. And I argue, actually, in the U.S. system, it's actually the biggest secret sauce that is right under our nose. Because I know what research there's a few other places, but not very. There's a couple of technical universities in Europe. There's a few in Asia, but actually they are so bad at entrepreneurship and all these other things. Like, our secret sauce are these places.
Yes. No, 100%.
Right? It's the MITs and the Stanfords and all that. In this political system, this is one of, for all of its interesting challenges, it's like the freedom to operate and the intellectual environment that it provides is one of the reasons why the U.S. has basically won every technological development war that is, maybe calling wars, race basically between them, right? And we are in peril of, in fact, losing that. There was one other technical question that you had asked about, which was what?
I think that was Mike's question.
I was going to ask about how the ITER design decisions got made and stuff, but I think we should just do a second one because I think
it's easy. ITER's design decision were made. It was simple. It was because of the limitation of the superconducting magnets. So ITER is exactly the size it needs to be because of the maximum magnetic field that technology can make. And then everything stems from that. All of the difficulties of the political arrangement, the payment arrangement, the governance arrangement, it all comes down to scale, right? And it came down to scale because you had to build it at that enormous size. That's the problem. And what I mean by enormous size, you have to construct the largest crane ever built by humanity to lift the pieces of it. That's why.
It's like a big corporate company.
It's actually
Versus,
not a company, and that's actually one of the other things of it. And that was it was a great question, like why a company and all this. And there were a variety of other practical reasons, like it was the only pathway for us to gain the resources to do it. But in the end, it's easy. It's because ITER as an organization can never deliver, even if it had the new technology. In fact, I had a great debate about this with somebody. It's like, the problem is its purpose. The purpose of that thing is not to deliver economic fusion power. It's to deliver a science product. And those two aren't completely decoupled from each other, but its purpose matters, right? And that actually goes to this other overall conversation about what we do as scientists and about what this means about how we intersect with the commercial world, right?
I mean, in some sense, people are always nostalgic for the Manhattan Project, right? So there's like a lot of nostalgia about, oh, let's get all the greatest scientists together with a lot of government funding. But there was the pressure of World War II in that case. So,
yes.
It had to be done in 4 years, whereas like ITER, that only has to be done in 30, which is longer. It's almost longer than a single career. So you can go through the whole process and never see the end. And if you create a lot of problems, maybe you're already retired by the time people.
I mean, again, like interacting with you guys as young scientists, I can tell you it was one of the reasons I almost left fusion. Right? I could see my students were not interested in it anymore, because anybody who could put two and two together realized it was going to be generational before. So it's like, I'm really going to wait around for like 30 years to see the first results of that experiment? No. And so one of the reasons for starting the company and starting this new effort was it was a re-engagement of a new generation of fusion scientists, which I take great pride in as well too. Like that there's a reason why it stemmed from classes, right? And it stemmed from those interactions that came and empowering actually young people to do those things. Unfortunately, I would just say about how much that proved to be true around ITER. Unfortunately, that was the other part to me, is it just drove me bananas. It's like, so you're telling me fusion is really one of the most important, because on paper it can basically solve everything of our energy problem forever. So it's such an important thing. We have one single project in the entire world, and if it fails, then we're toast. Right. That makes no freaking sense.
In terms of risk management or
care.
any decision making, that's not how you would structure it.
You never, ever, ever would do it that way. And in fact, that's the other cool part now that's happened because of the success of Combo Fusion, is that now fusion itself is diversified because there are other shots on goal with the other ones. So even though I started Combo Fusion Systems, the other greatest things was seeing like other things trying it, of course, right? What was the other part you said about ITER, Michael?
Oh, just about the kind of how, I'm trying to remember. Yeah, maybe like how the goal was set based on the technology at the time versus when did the insight about the B field happen versus the ITER timeline versus...
here's the irony of that. That insight was known before ITER was even started to be constructed. I have an entire talk, which actually, because this is when we came out with the idea. So this was called the high field path. It was actually known to everybody. Guess who started it? MIT. That this was what was at MIT. You know why? Because again, it was interesting, the circumstances of that, because there was the National High Field Magnet Laboratory, which was there. And so back in the 1970s, in fact, the PSFC was born, a very MIT thing. It was this insight as to, because the tokamak was invented around 1968 by the Soviets. By the early 1970s, those simple descriptions of what I said, it's like, oh yeah, that's probably true. Here's what will happen: as we increase the field, we can decrease the sizes of the devices. How do we make high magnetic fields? Oh, good. There's this guy called Francis Bitter who's ran this laboratory at MIT for the last 25 years. Fusion physicists knew almost nothing about magnets. And it's like, so here comes these amazing magnet engineers. And people said, oh yeah, so if you can take these things called Bitter coils and things like that, real, just like ingenious pieces of engineering. And what you do is you try to make magnetic fields which are on the order of 20 Tesla, peak magnetic fields. Oh, we can do that. Why? Really, really hard, because you're using copper plates. The amount of power dissipation scales like the magnetic field squared, because it scales like the current squared. You have to have really clever cooling techniques. Oh, you can probably only In fact, you can probably only keep these on for a couple seconds at a time. It turns out that that's fast enough. You have to have incredible structural engineering because the internal forces on these are, you asked about that, are immense, right? But you can only do that in copper coils. You end up having cryogenically cooled copper coils. That's what we ran at MIT for 30 plus years. That came from the merger of, in fact, the magnet lab and people who were expert basically from physics about the fusion, about what was going on. But everybody knew it was a dead end because it used copper coils. And when you use copper coils, you use resistive coils, the power that you put into the coils was going to exceed the amount of fusion power you ever get by factors of 10. So it was a scientific curiosity, basically, right? Because everyone knew you had to use superconducting coils. And so what was interesting is that there was a big argument in the field. It's just like, well, yeah, but if we build it out of copper coils, it's going to be like 20 to 30 times less expensive than ITER. And what in the end won was, because it was a political argument, they decided to build ITER instead. So the hilarity of this is that Spark could have been built with copper magnets 25 years ago. In fact, people from MIT led the designs of many of those. In fact, that had all cooled down by the time I came to MIT in the early 2000s. But many of my colleagues actually designed those devices. And the fact is, we would have already the scientific answers about high energy gaining systems in these systems. And what we would have done was built right away the power plant.
Right.
You just would have skipped Spark because it basically had answered those questions. Then what you would need to do is get the new magnet, because guess what happens is that everybody knows you can't make superconducting magnets at 20 Tesla, and then all of a sudden you could.
Yes.
Right? And it was a quantum leap in the ability to be able to do those things. So it's interesting is that I gave this talk because it was basically telling my colleagues, we screwed up. It wasn't that ITER was a scientific error, it was a tactical error, which is different. And if we just would have gone down this other pathway, guess what? This other technology would have emerged. But if you go down this is fascinating about big science, by the way, as well too. If you went down that other pathway, if it takes 30 years to build, to organize, to design, organize, fund, and build, it's going to be out of date in terms of technology by definition.
And you need to be somewhat speculative and have a risk appetite to factor that in to make predictions.
And risk appetite about how you distribute risk and about the things about how you do that and stay nimble around those different things. It's all tactical, right? It's informed by the science reality, but it still is very tactical. And the fact that no one in the world built one of those, that's actually why we have to build Spark.
Right. But it's exactly these stories that we find extremely fascinating, because this is not what you see in the papers. You see the science publications, but this is so essential to getting the good results, to retaining the people in the field, to actually get to also the scientific goal.
Right. And in fact, what's interesting is that we tend to devalue the opinion of young people too much in these tactical and strategic decisions. And it's interesting because it's another part of scientific and programmatic leadership. It sits with, in many ways, the people who are making the decisions. It impacts them the least because all the people who made those decisions and all that, unfortunately, many of them have passed away now, and certainly, or they're retired. It's like there's something about owning the consequences of your decisions, right? Yeah. Very important. Yeah. So in the end, that was, by the way, that was the other part. And everybody does ask me that. Oh, that fusion, Manhattan Project, Apollo Project, let's make this happen. No. It's because in many ways, we've already done that. The fact that in 1970, we didn't know shit about containing thermonuclear plasmas. And the fact is, remember now I said we've got 6 that have basically gotten there, right? Tokamak is the leading one, but there's other ones which are there. We've accomplished incredible scientific insight. And when I describe these things, realize this is on decades of just like sweat and toil and amazing science, which is underneath that. And it's just like, we did those things already. That's not the argument about what we're doing. What we're doing is trying to create an economic product that changes the world. That's not the Manhattan Project. That's not the Apollo Project. Those were things which were driven by other kinds of needs, right? This all goes to intent, right? If your intent is building an economic product, one, you must have companies because they're the only thing that actually make those. But two, then it's about how you engage the broader spectrum of talent about what you're working towards. It's not a scientific accomplishment. It's an economic accomplishment. We have not made the turn yet in fusion. That's why I'm spending almost all of my time, not in the sense talking about technical things, but about economic things, because turns out, it changes how you, again, it goes back to the tactics, right? Manhattan Project and Apollo Project, their tactics were not about building economic prosperity. That's what this has to do.
All right. No, this has been extremely fascinating. This has been very, very enjoyable discussion.
Yeah, I think it's such a deep topic that I think people really enjoy it, actually. In like the 2016 era, I was thinking like, oh, should I go work on fusion? I ended up working on semiconductors instead. But I was thinking about it, and there wasn't much material online. I started looking for lectures. I found like one or two by you, one or two by some other people. But they're actually, at the time, it was very hard to get an idea of what the edge of the field was from the outside. So I think it's awesome to get information out there. Since then, there's been more, but it's such an important problem.
And it's misunderstood too. And actually, in academia itself, I literally wrote a paper last year that says we are actually not approaching, it's not even these other things like tech transfer, just like our academic system is not geared to supporting this. Let's get our act together and actually do that. And it's because it's basically a plasma physics science program which is important. What we need is like this much, like actually, basically right now it's easy. We have three major things, right? One of them is financial resources. The second one is new organizational structures. And the third one is, because it's always that, it's talent. It's the rate of new talent, like getting guys like you excited or engaged in fusion because you realize, and all those three go together because you have to provide structural pathways to actually have young people engage and then really define, importantly, what are the opportunities and what you're working towards, which we still are struggling with so much. It's interesting for me. I was having, not a debate, a conversation with my daughter and my wife today. Can universities actually adapt fast enough, in fact, to make this work? Do we need other kinds of... People are asking these questions, right? There's people starting new universities, which is, in a way, it's trying to be responsive to things that we're not doing well inside of the traditional university academic environment.
Yeah, thank you so much for taking time on a Sunday. It was great meeting you.